In book one of the series, The Biggest Ideas in the Universe, called Space Time Motion, you take on classical mechanics, general relativity, by taking on the main equation of general relativity and making it accessible, easy to understand. So, maybe at the high level, what is general relativity? What's a good way to start to try to explain it?
Probably the best way to start to try to explain it is special relativity, which came first, 1905. It was the culmination, right, of many decades of people putting things together, but it was Einstein in 1905. In fact, it wasn't even Einstein. I should give more credit to Minkowski in 1907. So Einstein in 1905 figured out that you could get rid of the ether, the idea of a rest frame for the universe, and all the equations of physics would make sense, with the speed of light being a maximum. But then it was Minkowski, who used to be Einstein's professor in 1907, who realized the most elegant way of thinking about this idea of Einstein's was to blend space and time together into space time, to really imagine that there is no hard and fast division of the four-dimensional world in which we live into space and time separately. Einstein was at first dismissive of this. He thought it was just like, oh, the mathematicians are over formalizing again. But then he later realized that if space time is a thing, it can have properties. And in particular, it can have a geometry. It can be curved from place to place. And that was what let him solve the problem of gravity. He had previously been trying to fit in what we knew about gravity from Newtonian mechanics, the inverse square law of gravity, to his new relativistic theory. It didn't work. So the final leap was to say gravity is the curvature of space-time. And that statement is basically general relativity.
And the tension with Minkowski was he was a mathematician.
Yes.
So it's the tension between physics and mathematics. In fact, in your lecture about this equation, one of them, you say that Einstein is a better physicist than he gets credit for.
Yep. I know that's hard. That's a little bit of a joke there, right?
Yeah.
Because we all give Einstein a lot of credit, but then we also, partly based on fact, but partly to make ourselves feel better, tell ourselves a story about how later in life Einstein couldn't keep up. There were younger people doing quantum mechanics and quantum field theory and particle physics, and he was just sort of unable to really philosophically get over his objections to that. And I think that story about the latter part is completely wrong, like almost 180 degrees wrong. I think that Einstein understood quantum mechanics as well as anyone, at least up through the 1930s. I think that his philosophical objections to it are correct. So he should actually have been taken much more seriously about that. And what he did, what he achieved in trying to think these problems through, is to really basically understand the idea of quantum entanglement, which is kind of important these days when it comes to understanding quantum mechanics. Now, it's true that in the 40s and 50s, he placed his efforts in hopes for unifying electricity and magnetism with gravity that didn't really work out very well. All of us, try things that don't work out. I don't hold that against him. But in terms of IQ points, in terms of trying to be a clear thinking physicist, he was really, really great.
What does greatness look like for a physicist? So how difficult is it to take the leap from special relativity to general relativity? How difficult is it to imagine that, to consider space-time together and to imagine that there's a curvature to this whole thing?
Yeah, that's a great question. I think that if you want to make the case for Einstein's greatness, which is not hard to do, there's two things you point at. One is in 1905, his famous miracle year, he writes three different papers on three wildly different subjects, all of which would make you famous just for writing that one paper. Special relativity is one of them. Brownian motion is another one, which is just, the little vibrations of tiny little dust specks in the air. But who cares about that? What matters is it proves the existence of atoms. He explains Brownian motion by imagining there are molecules in the air and deriving their properties. Brilliant. And then he basically starts the world on the road to quantum mechanics with his paper on, which again is given a boring label of the photoelectric effect, What it really was is he invented photons. He showed that light should be thought of as particles as well as waves. And he did all three of those very different things in 1 year. Okay. But the other thing that gets him genius status is, like you say, general relativity. So this takes 10 years from 1905 to 1915. He wasn't only doing general relativity, he was working on other things. He invented a refrigerator, he did various interesting things. And he wasn't even the only one working on the problem. There were other people who suggested relativistic theories of gravity, but he really applied himself to it. And I think, as your question suggests, the solution was not a matter of turning a crank. It was something fundamentally creative. In his own telling of the story, his greatest moment, his happiest moment, was when he realized that, if the way that we would say it in modern terms, if you were in a rocket ship accelerating at 1 g, at one acceleration due to gravity, if the rocket ship were very quiet, you wouldn't be able to know the difference between being in a rocket ship and being on the surface of the Earth. Gravity is sort of not detectable, or at least not distinguishable from acceleration. So number one, that's a pretty clever thing to think. But number two, if you or I had had that thought, we would have gone, we're pretty clever. He reasons from there to say, okay, if gravity is not detectable, then it can't be like an ordinary force, right? The electromagnetic force is detectable. We can put charged particles around. Positively charged particles and negatively charged particles respond differently to an electric field or to a magnetic field. He realizes that what his thought experiment showed, or at least suggested, is that gravity isn't like that. Everything responds in the same way to gravity. How could that be the case? And then this other leap he makes is, it's because it's the curvature of space-time, right? It's a feature of space-time. It's not a force on top of it. And the feature that it is curvature. And then finally, he says, okay, clearly I'm going to need the mathematical tools necessary to describe curvature. I don't know them, so I will learn them. And they didn't have MOOCs or AI helpers back in those days. He had to sit down and read the math papers, and he taught himself differential geometry and invented general relativity.
What about the step of including time as just another dimension? So combining space and time. Is that a simple mathematical leap, as Minkowski suggested?
It's certainly not simple, actually. It's a profound insight. That's why I said I think we should give Minkowski more credit than we do. He's the one who really put the finishing touches on special relativity. Again, many people had talked about how things change when you move close to the speed of light, what Maxwell's equations of electromagnetism predict, and so forth, what their symmetries are. So people like Lorentz and Fitzgerald and Poincaré, there's a story that goes there. And in the usual telling, Einstein sort of puts the capstone on it. He's the one who says, all of this makes much more sense if there just is no ether. It is undetectable. We don't know how fast. Everything is relative, thus the name relativity. But he didn't take the actual final step, which was to realize that the underlying structure that he had invented is best thought of as unifying space and time together. I honestly don't know what was going through Minkowski's mind when he thought that. I'm not sure if he was, so mathematically adept that it was just clear to him, or he was really struggling it and he did trial and error for a while. I'm not sure.
I mean, do you, for him or for Einstein, visualize the four-dimensional space, try to play with the idea of time as just another dimension?
Oh, yeah, all the time. I mean, we, of course, make our lives easy by ignoring two of the dimensions of space. So instead of four-dimensional space-time, we just draw pictures of one dimension of space, one dimension of time, the so-called space-time diagram. But, maybe this is lurking underneath your question, but even the best physicists will draw, a vertical axis and a horizontal axis, and they'll go space, time. But deep down, that's wrong because you're sort of preferring one direction of space and one direction of time. And it's really the whole two-dimensional thing that is space-time. The more legitimate thing to draw on that picture are rays of light, are light cones. From every point, there is a fixed direction at which the speed of light would represent. And that is actually inherent in the structure. The division into space and time is something that's easy for us human beings.
What is the difference between space and time from the perspective of general relativity?
It's the difference between X and Y when you draw axes on a piece of paper.
So there's really no difference.
There's almost no difference. There's one difference that is kind of important, which is the following. If you have a curve in space, I'm going to draw it horizontally because that's usually what we do in space-time diagrams. If you have a curve in space, you've heard the motto before that the shortest distance between 2 points is a straight line. If you have a curve in time, which is, by the way, literally all of our lives, right? We all evolve in time. So you can start with one event in space-time and another event in space-time. What Minkowski points out is that the time you measure along your trajectory in the universe is precisely analogous to the distance you travel on a curve through space. And by precisely, I mean it is also true that the actual distance you travel through depends on your path, right? You can go a straight line, shortest distance, you can curvy line to be longer. The time you measure in space-time, the literal time that ticks off on your clock, also depends on your path. But it depends on it the other way, so that the longest time between 2 points is a straight line. And if you zig back and forth in space-time, you take less and less time to go from point A to point B.
How do we make sense of that? The difference between the observed reality and the objective reality underneath it? Or is objective reality a silly notion, given general relativity?
I'm a huge believer in objective reality. I think that objective reality objectively is real.
Yeah.
But I do think that people kind of are a little overly casual about the relationship between what we observe and objective reality in the following sense. Of course, in order to explain the world, our starting point and our ending point is our observations, our experimental input, the phenomena we experience and see around us in the world. But in between, there's a theory. There's a mathematical formalization of our ideas about what is going on. And if a theory fits the data and is very simple and makes sense in its own terms, then we say that the theory is right. And that means that we should attribute some reality to the entities that play an important role in that theory, at least provisionally until we come up with a better theory down the road.
I think a nice way to test the difference between objective reality and the observed reality is what happens at the edge of the horizon of a black hole. So technically, as you get closer to that horizon, time stands still.
Yes and no.
Okay.
It depends on exactly how careful we're being. So here is a bunch of things I think are correct. If you imagine there is a black hole space-time, so like the whole solution to Einstein's equation, and you treat you and me as what we call test particles. So we don't have any gravitational fields ourselves. We just move around in the gravitational field. And that's obviously an approximation, okay? But let's imagine that. And you stand outside the black hole and I fall in. And as I'm falling in, I'm waving to you, because I'm going into the black hole. You will see me move more and more slowly. And also the light from me is redshifted. So I kind of look embarrassed because I'm falling into a black hole. And there is a limit. There's a last moment that light will be emitted from me, from your perspective, forever. Okay. Now you don't literally see it because I'm emitting photons more and more slowly, right? Because from your point of view. So it's not like I'm equally bright. I basically fade from view in that picture. Okay. So that's one approximation. The other approximation is I do have a gravitational field of my own. And therefore, as I approach the black hole doesn't just sit there and let me pass through. It kind of moves out to eat me up because its net energy mass is going to be mine plus its. But roughly speaking, yes, I think so. I don't like to go to the dramatic extremes because that's where the approximations break down. But if you see something falling into a black hole, you see its clock ticking more and more slowly.
How do we know it fell in?
We don't. I mean, how would we? Because it's always possible that right at the last minute, it had a change of heart and starts accelerating away, right? If you don't see it pass in, you don't know. And let's point out that as smart as Einstein was, he never figured out black holes, and he could have. It's kind of embarrassing. It took decades for people thinking about general relativity to understand that there are such things as black holes, because basically Einstein comes up with general relativity in 1915. 2 years later, Carl Schwarzschild, derives the solution to Einstein's equation that represents a black hole, the Schwarzschild solution. No one recognized it for what it was until the 50s, David Finkelstein and other people. And that's just, one of these examples of physicists not being as clever as they should have been.
Well, that's the singularity. That's the kind of the edge of the theory, the limit. So it's understandable that it's difficult to imagine the limit of things.
It is absolutely hard to imagine, and a black hole is very different in many ways from what we're used to. On the other hand, the real reason, of course, is that between 1915 and 1955, there's a bunch of other things that are really interesting going on in physics, all of particle physics and quantum field theory. So many of the greatest minds were focused on that. But still, if the universe hands you a solution to general relativity in terms of curved spacetime, and it's kind of mysterious, certain features of it, I would put some effort into trying to figure it out.
So how does a black hole work? Put yourself in the shoes of Einstein and take general relativity to its natural conclusion about these massive things.
It's best to think of a black hole as not an object so much as a region of space-time, okay? It's a region with the property, at least in classical general relativity. Quantum mechanics makes everything harder, but let's imagine we're being classical for the moment. It's a region of space-time with the property that if you enter, you can't leave. Literally, the equivalent of escaping a black hole would be moving faster than the speed of light. They're both precisely equally difficult. You would have to move faster than the speed of light to escape from the black hole. So once you're in, that's fine. In principle, you don't even notice when you cross the event horizon, as we call it. The event horizon is that point of no return, where once you're inside, you can't leave. But meanwhile, the space-time is sort of collapsing around you to ultimately a singularity in your future, which means that the gravitational forces are so strong they tear your body apart, and you will die in a finite amount of time. The time it takes, if the black hole is about the mass of the sun, to go from the event horizon to the singularity takes about 1/1,000,000th of a second.
And what happens to you if you fall into the black hole? Like, if we think of an object as information, that information gets destroyed.
Well, you've raised a crucially difficult point. So that's why I keep needing to distinguish between black holes according to Einstein's theory of general relativity, which is book one of Spacetime and Geometry, which is perfectly classical. And then come the 1970s, we start asking about quantum mechanics and what happens in quantum mechanics. According to classical general relativity, the information that makes up you when you fall into the black hole is lost to the outside world. It's there, it's inside the black hole, but we can't get it anymore. In the 1970s, Stephen Hawking comes along and points out that black holes radiate. They give off photons and other particles to the universe around them, and as they radiate, they lose mass, and eventually they evaporate, they disappear. So once that happens, I can no longer say the information about you or a book that I threw in the black hole or whatever is still there, is hidden behind the black hole because the black hole has gone away. So either that information is destroyed, like you said, or it is somehow transferred to the radiation that is coming out, to the Hawking radiation. The large majority of people who think about this believe that the information is somehow transferred to the radiation and information is conserved. That is a feature both of general relativity by itself and of quantum mechanics by itself. So when you put them together, that should still be a feature. We don't know that for sure. There are people who have doubted it, including Stephen Hawking for a long time. But that's what most people think. And so what we're trying to do now in a topic which has generated many, many hundreds of papers called the black hole information loss puzzle is figure out how to get the information from you or the book into the radiation that is escaping the black hole.
Is there any way to observe Hawking radiation to a degree where you can start getting insight? Or is this all just in the space of theory right now?
Right now, we are nowhere close to observing Hawking radiation. Here's the sad fact. The larger the black hole is, the lower its temperature is. So a small black hole, like a microscopically small black hole, might be very visible. It's given off light. But something like the black hole at the center of our galaxy, 3 million times the mass of the sun or something like that, Sagittarius A star, that is so cold and low temperature that its radiation will never be observable. Black holes are hard to make. We don't have any nearby. The ones we have out there in the universe are very, very faint. So there's no immediate hope for detecting Hawking radiation.
Allegedly, we don't have any nearby.
As far as we know, we don't have any nearby.
Could tiny ones be hard to detect? Somewhere at the edges
Absolutely.
of the solar system, maybe?
So you don't want them to be too tiny or they're exploding, right? Or they're very bright and then they would be visible. But there's absolutely a regime where black holes are large enough not to be visible because the larger ones are fainter, right? Not giving off radiation, but small enough to not been detected through their gravitational effect. Yeah.
Psychologically, just emotionally, how do you feel about black holes? They scare you?
I love them. I love black holes. But the universe weirdly makes it hard to make a black hole, right? Because you really need to squeeze an enormous amount of matter and energy into a very, very small region of space. So we know how to make stellar black holes. A supermassive star can collapse to make a black hole. We know we also have these supermassive black holes at the center of galaxies. We're a little unclear where they came from. I mean, maybe stellar black holes that got together and combined, but that's one of the exciting things about new data from the James Webb Space Telescope is that quite large black holes seem to exist relatively early in the history of the universe. So it was already difficult to figure out where they came from. Now it's an even tougher puzzle.
So these supermassive black holes are formed somewhere early on in the universe. I mean, that's a feature, not a bug, right? That we don't have too many of them. Otherwise, we wouldn't have the time or the space to form the little pockets of complexity that we call humans.
I think that's fair. Yeah. It's always interesting when something is difficult but happens anyway, right? I mean, the probability of making a black hole could have been 0. It could have been 1, but it's this interesting number in between, which is kind of fun.
Are there more intelligent alien civilization than there are supermassive black holes?
Yeah. I have no idea, but I think your intuition is right that it would have been easy for there to be lots of civilizations and then we would have noticed them already. And we haven't. So absolutely the simplest explanation for why we haven't is that they're not there.
Yeah. I just think it's so easy to make them, though. So there must be, I understand that's the simplest explanation, but also,
how easy is it to make life or eukaryotic life or multicellular life?
it seems like life finds a way. Intelligent alien civilizations, sure, maybe there is somewhere along that chain a really, really hard leap. But once you start life, once you get the origin of life, it seems like life just finds a way everywhere, in every condition. It just figures it out.
I mean, I get it. I get exactly what you're thinking. I think it's a perfectly reasonable attitude to have before you confront the data. I would not have expected Earth to be special in any way. I would have expected there to be plenty of very noticeable extraterrestrial civilizations out there. But even if life finds a way, even if we buy everything you say, how long does it take for life to find a way? What if it typically takes 100 billion years? Then we'd be alone.
So it's a time thing. So to you, really, there's most likely there's no alien civilizations out there. I can't see it. I believe there's a ton of them, and there's another explanation why we can't see them.
I don't believe that very strongly. Look, I'm not going to place a lot of bets here. I would not. I'm both pretty up in the air about whether or not life itself is all over the place. It's possible when we visit other worlds, other solar systems, there's very tiny microscopic life ubiquitous, but none of it has reached some complex form. It's also possible there isn't any. It's also possible that there are intelligent civilizations that have better things to do than knock on our doors. So I think we should be very humble about these things we know so little about.
And it's also possible there's a great filter where there's something fundamental about once a civilization develops complex enough technology, that technology is more statistically likely to destroy everybody versus to continue being creative.
That is absolutely possible. I'm actually putting less credence on that one just because you need it to happen every single time, right? Mm-hmm. If even one, I mean, this goes back to John von Neumann pointed out that you don't need to send the aliens around the galaxy. You can build self-reproducing probes and send them around the galaxy. And you might think, well, the galaxy is very big. It's really not. It's some tens of thousands of light years across and billions of years old. So you don't need to move at a high fraction the speed of light to fill the galaxy.
So if you were an intelligent alien civilization, the dictator of one, you would just send out a lot of probes, self-replicating probes.
100%. And
just spread out.
yes. And what you should do, so if you want the optimistic spin, here's the optimistic spin. People looking for intelligent life elsewhere often tune in with their radio telescopes, right? At least we did before Arecibo was decommissioned. That's not a very promising way to find intelligent life elsewhere, because why in the world would a super intelligent alien civilization waste all of its energy by beaming it in random directions into the sky? For one thing, it just passes you by, right? So if we're here on Earth, we've only been listening to radio waves for a couple hundred years, okay? So if an intelligent alien civilization exists for 1 billion years, they have to pinpoint exactly the right time to send us this signal. It is much, much more efficient to send probes and to park, to go to the other solar systems, just sit there and wait for an intelligent civilization to arise in that solar system. This is kind of the 2001 monolith hypothesis, right? I would be less surprised to find a sort of quiescent alien artifact in our solar system than I would to catch a radio signal from an intelligent civilization.
So you're a sucker for in-person conversations versus remote.
I just want to integrate over time. A probe can just sit there and wait, whereas a radio wave goes right by you.
How hard is it for an alien civilization, again, you're the dictator of one, to figure out a probe that is most likely to find a common language with whatever it finds?
Couldn't I be like the elected leader of
elected
the alien
leader,
civilization?
democratic leader, elected leader of a democratic alien civilization? Yes,
I think we would figure out that language thing pretty quickly. I mean, maybe not as quickly as we do when different human tribes find each other, because obviously there's a lot of commonalities in humanity, but there is logic and math, and there is the physical world. You can point to a rock and go, rock, right? I don't think it would take that long. I know that Arrival, the movie, based on a Ted Chiang story, suggested that the way that aliens communicate is going to be fundamentally different. But also they had precognition and other things I don't believe in. So I think that if we actually find aliens, that will not be our long-term problem.
So there's a folks, one of the places you're affiliated with is Santa Fe, and they approach the question of complexity in many different ways and ask the question in many different ways of what is life, thinking broadly. So to you would be able to find it. You'll think you show up, a probe shows up to a planet, we'll see a thing and be like, yeah, that's a living thing.
Well, again, if it's intelligent and technologically advanced, the more short-term question of if we get, some spectroscopic data from an exoplanet, so we know a little bit about what is in its atmosphere, how can we judge whether or not that atmosphere is giving us a signature of life existing? That's a very hard question that people are debating about. I mean, one very simple-minded but perhaps interesting approach is to say small molecules don't tell you anything, because even if life could make them, something else could also make them. But long molecules, that's the kind of thing that life would produce.
So signs of complexity. I don't know. I just have this nervous feeling that we won't be able to detect it. We'll show up to a planet, there'll be a bunch of liquid on it. We take a swim in the liquid, and we won't be able to see the intelligence in it. Whether that intelligence looks like something like, ants, or we'll see movement, perhaps strange movement, but we won't be able to see the intelligence in it or communicate with it. I guess if we have nearly infinite amount of time to play with different ideas, we might be able to.
I'm in favor of this kind of humility, this intellectual humility that we won't know, because we should be prepared for surprises. But I do always keep coming back to the idea that we all live in the same physical universe. And let's put it this way. the development of our intelligence has certainly been connected to our ability to manipulate the physical world around us. And so I would guess, without 100% credence by any means, but my guess would be that any advanced kind of life would also have that capability. Both dolphins and octopuses are potential counterexamples to that. But I think in the details, there would be enough similarities that we would recognize it.
I don't know how we got on this topic, but I think it was from supermassive black holes. So if we return to black holes and talk about the holographic principle more broadly, you have a recent paper on the topic. You've been thinking about the topic in terms of rigorous research perspective and just as a popular book writer. So what is the holographic principle?
Well, it goes back to this question that we were talking about with the information and how it gets out. In quantum mechanics, certainly, arguably even before quantum mechanics comes along in classical statistical mechanics, there's a relationship between information and entropy. Entropy is my favorite thing to talk about, that I've written books about and will continue to write books about. So Hawking tells us that black holes have entropy. And it's a finite amount of entropy. It's not an infinite amount. But the belief is, and now we're already getting quite speculative, the belief is that the entropy of a black hole is the largest amount of entropy that you can have in a region of space-time. It's sort of the most densely packed that entropy can be. And what that means is there's sort of a maximum amount of information that you can fit into that region of space, and you call it a black hole. And interestingly, you might expect if I have a box and I'm going to put information in it, and I don't tell you how I'm going to put the information in, but I ask, how does the information I can put in scale with the size of the box? You might think, well, it goes as the volume of the box because the information takes up some volume and I can only fit in a certain amount. And that is what you might guess for the black hole, but it's not what the answer is. The answer is that the maximum information, as reflected in the black hole entropy, scales as the area of the black hole's event horizon, not the volume inside. So people thought about that in both deep and superficial ways for a long time, and they proposed what we now call the holographic principle, that the way that space-time and quantum gravity convey information or hold information is not different bits or qubits for quantum information at every point in space-time. It is something holographic, which means it's sort of embedded in or located in or can be thought of as pertaining to one dimension less of the three dimensions of space that we live in. So in the case of the black hole, the event horizon is two-dimensional, embedded in a three-dimensional universe. And the holographic principle would say all of the information contained in the black hole can be thought of as living on the event horizon rather than in the interior of the black hole. I need to say one more thing about that, which is that this was an idea. What that idea I just told you was the original holographic principle put forward by people like Gerard de Tooft and Leonard Susskind, super famous physicist. Leonard Susskind was on my podcast and gave a great talk. He's very, very good at explaining these things.
Mindscape podcast. Everybody should listen.
That's right. Yes.
And you don't just have physicists on.
I don't.
I love Mindscape.
Oh, thank you very much.
Curiosity driven.
Yeah, ideas.
Exploration of ideas.
From smart people, yeah. But anyway, what I was trying to get at was Susskind and also at Tooft were a little vague. They were a little hand-wavy about holography and what it meant. Where holography, the idea that information is sort of encoded on a boundary really came into its own was with Juan Maldacena in the 1990s. And the ADS-CFD correspondence, which we don't have to get into any detail, but it's a whole full-blown theory of, it's two different theories. One theory in n dimensions of space-time without gravity, and another theory in n+1 dimensions of space-time with gravity. And the idea is that this n-dimensional theory is, casting a hologram into the n+1 dimensional universe to make it look like it has gravity. And that's holography with a vengeance. And that's an enormous source of interest for theoretical physicists these days.
How should we picture what impact that has? The fact that you can store all the information you can think of as all the information that goes into a black hole can be stored at the event horizon.
Yeah, I mean, it's a good question. One of the things that quantum field theory indirectly suggests is that there's not that much information in you and me compared to the volume of space-time we take up. As far as quantum field theory is concerned, you and I are mostly empty space. And so we are not information dense, right? The density of information in us or in a book or a CD or whatever, computer RAM, is indeed encoded by volume. Like there's different bits located at different points in space, but that density of information is super duper low. So we're just like the speed of light or just like the Big Bang. For the information in a black hole, we are far away in our everyday experience from the regime where these questions become relevant. So it's very far away from our intuition. We don't really know how to think about these things. We can do the math, but we don't feel it in our bones.
So you can just write off that weird stuff happens in a
Well, we'd
black
like
hole.
to do better, but we're trying. I mean, that's why we have an information loss puzzle, because we haven't completely solved it. So here's just one thing to keep in mind. Once space-time becomes flexible, which it does according to general relativity, and you have quantum mechanics, which has fluctuations in virtual particles and things like that, the very idea of a location in space-time becomes a little bit fuzzy, right? Because it's flexible and quantum mechanics says you can't even pin it down. So information can propagate in ways that you might not have expected. And that's easy to say, and it's true, but we haven't yet come up with the right way to talk about it that is perfectly rigorous.
But it's crazy how dense with information a black hole is. And then plus, like, quantum mechanics starts to come into play. So, you almost want to romanticize the kind of interesting computation type things that are going on inside the black hole.
You do. But I'll point out one other thing. It's information dense, but it's also very, very high entropy. So a black hole is kind of like a very, very, very specific random number, right? It takes a lot of digits to specify it, but the digits don't tell you anything. They don't give you anything useful to work on. So it takes a lot of information, but it's not of a form that we can learn a lot from.
But hypothetically, I guess, as you mentioned, the information might be preserved. The information that goes into a black hole, it doesn't get destroyed. So what does that mean when the entropy is really high?
Well, the black hole, I said that the black hole is the highest density of information, but it's not the highest amount of information because the black hole can evaporate. And when it evaporates, and people have done the equations for this, when it evaporates, the entropy that it turns into is actually higher than the entropy of the black hole was, which is good because entropy is supposed to go up. But it's much more dilute, right? It's spread across a huge volume of space-time. So in principle, all that you made the black hole out of, the information that it took, is still there, we think, in that information, but it's scattered to the four winds.
We just talked about the event horizon of a black hole. What's on the inside? What's at the center of it?
No one's been there. So
I came back to
again,
tell.
this is a theoretical prediction. But I'll say one super crucial feature of the black holes that we know and love, the kind that Schwarzschild first invented. There's a singularity, but it's not at the middle of the black hole. Remember, space and time are parts of parts of one unified space-time. The location of the singularity in the black hole is not the middle of space, but our future. It is a moment of time. It is like a big crunch. The Big Bang was an expansion from a singularity in the past. Big crunch probably doesn't exist, but if it did, it would be a collapse to a singularity in the future. That's what the interiors of black holes are like. You can be fine in the interior, but things are becoming more and more crowded. Space-time is becoming more and more warped, and eventually you hit a limit, and that's the singularity in your future.
I wonder what time is like on the inside of a black hole.
Time always ticks by at 1 second per second. That's all it can ever do.
Yeah.
Time can tick by differently for different people. And so you have things like the twin paradox, where two people initially are the same age. One goes off near the speed of light and comes back. Now they're not. You can even work out that the one who goes out and comes back will be younger because they did not take the shortest distance path. But locally, as far as you and your wristwatch are concerned, time is not funny. Your neurological signals in your brain and your heartbeat and your wristwatch, whatever's happening to them, is happening to all of them at the same time. So time always seems to be ticking along at the same rate.
But if you fall into a black hole and then I'm an observer just watching it, and then you come out once it evaporates a million years later, I guess you'd be exactly the same age. Have you aged at all?
You would be converted into photons. You would not be you anymore.
Right. So it's not at all possible that information is preserved exactly as it went in.
It depends on what you mean by preserved. It's there in the microscopic configuration of the universe. It's exactly as if I took a regular book, made of paper, and I burned it. The laws of physics say that all the information in the book is still there in the heat and light and ashes. You're never going to get it as a matter of practice, but in principle, it's still there.
But what about the age of things from the observer perspective, from outside the black hole?
From outside the black hole, doesn't matter because they're inside the black hole.
No, so but isn't there? Okay, there's no way to escape the black hole,
right?
Except
to let it evaporate.
But
also, by the way, just in relativity, special relativity, forget about general relativity. It's enormously tempting to say, okay, here's what's happening to me right now. I want to know what's happening far away right now. The whole point of relativity is to say there's no such thing as right now when you're far away. And that is doubly true for what's inside a black hole. So you're tempted to say, well, how fast is their clock ticking? Or how old are they now? Not allowed to say that according to relativity.
Because space and time are treated the same, and so it doesn't even make sense.
That's
what happens to time in the holographic principle?
As far as we know, nothing dramatic happens. We're not anywhere close to being confident that we know what's going on here yet. So there are good unanswered questions about whether time is fundamental, whether time is emergent, whether it has something to do with quantum entanglement, whether time really exists at all, different theories, different proponents of different things. But there's nothing specifically about holography that would make us change our opinions about time, whatever they happen to be.
But holography is fundamentally about, it's a question of space.
It really is, yeah.
Okay, so time is just
time just goes along for the ride, as far as we know. Yeah.
So all the questions about time is just almost like separate questions, whether it's emergent and all that.
Yeah,
kind of stuff.
I mean that might be a reflection of our ignorance right now, but yes.
If we figure out a lot, millions of years from now about black holes, how surprised would you be if they travel back in time and told you everything you want to know about black holes? How much do you think there is still to know? And how mind-blowing would it be?
It does depend on what they would say. I think that there are colleagues of mine who think that we're pretty close to figuring out how information gets out of black holes, how to quantize gravity, things like that. I'm more skeptical that we are pretty close. I think that there's room for a bunch of surprises to come. So in that sense, I suspect I would be surprised. The biggest and most interesting surprise to me would be if quantum mechanics itself were somehow superseded by something better. As far as I know, there's no empirical evidence-based reason to think that quantum mechanics is not 100% correct. But it might not be. That's always possible. So, and there are, again, respectable friends of mine who speculate about it. So that's something that's the first thing I'd want to know.
Oh, so like the black hole would be the most clear illustration.
Yeah, that's where it would show up.
If there's something, it would show up there.
So, I mean, maybe. The point is that black holes are mysterious for various reasons. So, yeah, if our best theory of the universe is wrong, that might help explain why.
But do you think it's possible we'll find something interesting like black holes sometimes create new universes, or black holes are a kind of portal through space-time to another place or something like this? And then our whole conception of what is the fabric of space-time changes completely because black holes, it's like Swiss cheese type of situation.
Yeah, that would be less surprising to me because I've already written papers about that. We don't have, again, strong reason to think that the interior of a black hole leads to another universe. But it is possible, and it's also very possible that that's true for some black holes and not others. This is stuff we don't know. It's easy to ask questions we don't know the answer to. The problem is the questions that are easy to ask that we don't know the answer to are super hard to answer.
Because these objects are very difficult to test and to explore for us.
The regimes are just very far away. So either literally far away in space, but also in energy or mass or time or whatever.
You've published a paper on the holographic principle, or that involves the holographic
Hmm.
principle. What can you explain the details of that?
Yeah, I'm always interested in, since my first published paper, taking these wild speculative ideas and trying to test them against data. And the problem is when you're dealing with wild speculative ideas, they're usually not well defined enough to make a prediction, right? Like it's kind of I know what's going to happen in some cases, I don't know what's going to happen in other cases. So we did the following thing. As I've already mentioned, the holographic principle, which is meant to reflect the information contained in black holes, seems to be telling us that there's less information, less stuff that can go on than you might naively expect. So let's upgrade naively expect to predict using quantum field theory. Quantum field theory is our best theory of fundamental physics right now. Unlike this holographic black hole stuff, quantum field theory is entirely local. In every point of space, something can go on, and then you add up all the different points in space. Okay, not holographic at all. So there's a mismatch between the expectation for what is happening, even in empty space, in quantum field theory versus what the holographic principle would predict. How do you reconcile these two things? So there's one way of doing it that had been suggested previously, which is to say that in the quantum field theory way of talking, it implies there's a whole bunch more states, a whole bunch more ways the system could be than there really are.
Mm.
And the answer, and just I'll do a little bit of math, just because there might be some people in the audience who like the math. If I draw two axes on a two-dimensional geometry, like the surface of the table, right? You know that the whole point of it being two-dimensional is I can draw two vectors that are perpendicular to each other. I can't draw three vectors that are all perpendicular to each other, right? They need to overlap a little bit. That's true for any numbers of dimensions. But I can ask, okay, how much do they have to overlap? If I try to put more vectors into a vector space than the dimensionality of the vector space, can I make them almost perpendicular to each other? And the mathematical answer is, as the number of dimensions gets very, very large, you can fit a huge extra number of vectors in that are almost perpendicular to each other. So in this case, what we're suggesting is the number of things that can happen in a region of space is correctly described by holography. It is somewhat overcounted by quantum field theory, but that's because the quantum field theory states are not exactly perpendicular to each other. I should have mentioned that in quantum mechanics, states are given by vectors in some huge dimensional vector space, very, 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 very large dimensional vector space. So maybe the quantum field theory states are not quite perpendicular to each other. If that is true, that's a speculation already, but if that's true, how would you know? What is the experimental deviation? And it would have been completely respectable if we had gone through and made some guesses and found that there is no noticeable experimental difference because, again, these things are in regimes very, very far away. We stuck our necks out. We made some very, very specific guesses as to how this weird overlap of states would show up in the equations of motion for particles like neutrinos. And then we made predictions on how the neutrinos would behave on the basis of those wild guesses. And then we compared them with data. And what we found is we're pretty close, but haven't yet reached the detectability of the effect that we are predicting. In other words, well, basically one way of saying what we predict is if a neutrino, and there's reasons why it's neutrinos, we can go into if you want, but it's not that interesting. If a neutrino comes to us from across the universe, from some galaxy very, very far away, there is a probability as it's traveling that it will dissolve into other neutrinos because they're not really perpendicular to each other as vectors as they would ordinarily be in quantum field theory. And that means that if you look at neutrinos coming from far enough away with high enough energies, they should disappear. Like if you see if you see a whole bunch of nearby neutrinos, but then further away, you should see fewer. And there's an experiment called IceCube, which is this amazing testament to the ingenuity of human beings, where they go to Antarctica and they drill holes and they put photodetectors on a string a mile deep in these holes. And they basically use all of the ice in a cube, I don't know whether it's a mile or not, but it's like a kilometer or something like that, some big region, that much ice is their detector.
Hmm.
And they're looking for flashes when a cosmic ray or a neutrino or whatever hits ice molecule, water molecule in the ice.
With
Makes a
flashes
flash.
in the ice. They're looking
Yes,
for.
they're looking for flashes
But
in
isn't
the
there
ice.
some crazy? I mean, what does the detector of that look like?
It's a bunch of strings, many, many, many strings with 360-degree photodetectors.
Yeah,
And you will.
that's really cool.
It's extremely cool.
Yeah.
And they've done amazing work, and they find neutrinos.
So they're looking for neutrinos.
Yeah. So the whole point is most cosmic rays are protons. Because why? Because protons exist and they're massive enough that you can accelerate them to very high energies. So high energy cosmic rays tend to be protons. They also tend to hit the Earth's atmosphere and decay into other particles. So neutrinos, on the other hand, punch right through, at least usually, right, to a great extent. So not just Antarctica, but the whole Earth. Occasionally, a neutrino will interact with a particle here on Earth, and there's neutrinos going through your body all the time, from the sun, from the universe, etc. And so if you're patient enough and you have a big enough part of the Antarctic ice sheet to look at, it's the nice thing about ice is it's transparent. So you've built yourself, nature has built you a neutrino detector.
So
That's what
why
ice cube does?
Why ice? So is it just because of the low noise and you get to watch this thing and it's
much more dense than air, but it's transparent.
so yeah, much more dense, so higher probability, and then it's transparency, and then it's also in the middle of nowhere, so you can humans.
Well, that's
are
all you
great.
need. There's not that
I
much
love
ice, right? Yeah. So
Humans
there's
are
more
the
ice in
best.
Antarctica than anywhere else, right? So anyway, you can go and you can get a plot from the ice cube experiment.
Yeah.
How many neutrinos there are that they've detected with very high energies. And we predict in our weird little holographic guessing game that there should be a cutoff. You should see neutrinos as you get to higher and higher energies, and then they should disappear. If you look at the data, their data gives out exactly where our cutoff is. That doesn't mean that our cutoff is right. It means they lose the ability to do the experiment exactly where we predict the cutoff should be.
Oh boy. Okay. But why is there a limit?
Oh, just because there are fewer high energy neutrinos. So there's a spectrum and it goes down. But what we're plotting here is number of neutrinos versus energy. It's fading away and they just get very, very few.
And you need the high energy neutrinos for your prediction.
Our effect is a little bit bigger for higher energies. Yeah.
Got it. And that effect has to do with this almost perpendicular thing.
And let me just mention the name of Oliver Friedrich, who was a postdoc who led this. He deserves the credit for doing this. I was a co-author and a collaborator. I did some work, but he really gets the lion's share.
Thank you, Oliver. Thank you for pushing this wild science forward. Just to speak to that, the meta process of it, how do you approach asking these big questions and trying to formulate as a paper, as an experiment that could make a prediction, all that kind of stuff? What's your process?
There's a very interesting things that happens once you're a theoretical physicist, once you become trained. You're a graduate student, you've written some papers and whatever. Suddenly you are the world's expert in a really infinitesimally tiny area of knowledge, right? And you know not that much about other areas. There's an overwhelming temptation to just drill deep, right? Just keep doing basically the thing that you started doing. But maybe that thing you started doing is not the most interesting thing to the world or to you or whatever. So you need to separately develop the capability of stepping back and going, okay, now that I can write papers in that area, now that I'm sort of trained enough in the general procedure, what is the best match between my interests, my abilities, and what is actually interesting? And honestly, I've not been very good at that over my career. I have my process traditionally was I was working in this general area of particle physics, field theory, general relativity, cosmology, and I would sort of try to take things other people were talking about and ask myself whether or not it really fit together. Like my two, so I guess I have 3 papers that I've ever written that have done super well in terms of getting cited and things like that. One was my first ever paper that I get very little credit for. That was my advisor and his collaborator, set that up. The other 2 were basically my idea. One was right after we discovered that the universe was accelerating. So in 1998, observations showed that not only is the universe expanding, but it's expanding faster and faster. So that's attributed to either Einstein's cosmological constant or some more complicated form of dark energy, some mysterious thing that fills the universe. And people were throwing around ideas about this dark energy stuff. What could it be? And so forth. Most of the people throwing around these ideas were cosmologists. They work on cosmology. They think about the universe all at once. Since I like to talk to people in different areas, I was sort of more familiar than average with what a respectable working particle physicist would think about these things. And what I immediately thought was, you guys are throwing around these theories. These theories are wildly unnatural. They're super finely tuned. Like any particle physicist would just be embarrassed to be talking about this. But rather than just scoffing at them, I sat down and asked myself, okay, is there a respectable version? Is there a way to keep the particle physicists happy, but also make the universe accelerate? And I realized that there is some very specific set of models that is relatively natural. And guess what? You can make a new experimental prediction on the basis of those. And so I did that. People were very happy about that.
What was the thing that would make physicists happy, that would make sense of this fragile thing that people call dark energy?
So the fact that dark energy pervades the whole universe and is slowly changing, that should immediately set off alarm bells, because particle physics is a story of length scales and time scales that are generally, guess what? Small, right? Particles are small, they vibrate quickly, and you're telling me now I have a new field and its typical rate of change is once every billion years, right? Like that's just not natural. And indeed, you can formalize that and say, look, even if you wrote down a particle that evolved slowly over billions of years, if you let it interact with other particles at all, that would make it move faster. Its dynamics would be faster. Its mass would be higher, et cetera, et cetera. So there's a whole story. Things need to be robust and they all talk to each other in quantum field theory. So how do you stop that from happening? And the answer is symmetry. You can impose a symmetry that protects your new field from talking to any other fields, okay? And this is good for two reasons. Number one, it can keep the dynamics slow. So if you can't tell me why it's slow, you just made that up, but at least it can protect it from speeding up because it's not talking to any other particles. And the other is it makes it harder to detect. Naively, experiments looking for fifth forces or time changes of fundamental constants of nature like the charge of the electron, these experiments should have been able to detect these dark energy fields. And I was able to propose a way to stop that from happening.
The detection.
The detection, yeah. Because a symmetry could stop it from interacting with all these other fields and therefore makes it harder to detect. And just by luck, I realized, because it was actually based on my first ever paper, there's one loophole. If you impose these symmetries, so you protect the dark energy field from interacting with any other fields, there's one interaction that is still allowed that you can't rule out. And it is a very specific interaction between your dark energy field and photons, which are very common. And it has the following effect. As a photon travels through the dark energy, the photon has a polarization, up, down, left, right, whatever it happens to be. And as it travels through the dark energy, that photon will rotate its polarization. This is called birefringence. And you can kind of run the numbers and say, you can't make a very precise prediction because we're just making up this model. But if you want to roughly fit the data, you can predict how much polarization rotation there should be. A couple of degrees, okay? Not that much. So that's very hard to detect. People have been trying to do it. Right now, literally, we're on the edge of either being able to detect it or rule it out using the cosmic microwave background. And there is just, truth in advertising. There is a claim on the market that it's been detected, that it's there. It's not very statistically significant. If I were to bet, I think it would probably go away. It's a very hard thing to observe. But maybe as you get better and better data, cleaner and cleaner analysis, it will persist and we will have directly detected the dark energy.
So if we just take this tangent of dark energy, people will sometimes bring up dark energy and dark matter as an example why physicists have lost it, lost their mind. We're just going to say that there's this field that permeates everything, is unlike any other field, and it's invisible. And it helps us work out some of the math. How do you respond to that? Those kinds of suggestions?
Well, two ways. One way is those people would have had to say the same thing when we discovered the planet Neptune.
Yeah.
Because it's exactly analogous, where we have a very good theory, in that case, Newtonian gravity in the solar system. We made predictions. The predictions were slightly off for the motion of the outer planets. You found that you could explain that motion by positing something very simple, one more planet in a very, very particular place. And you went and looked for it, and there it was, right? That was the first successful example of finding dark matter in the universe.
It's a matter that we can't see.
Neptune was dark.
Yeah.
There's a difference between dark matter and dark energy, right? Dark matter, as far as we are hypothesizing it, is a particle of some sort. It's just a particle that interacts with us very weakly. So we know how much of it there is. We know more or less where it is. We know some of its properties. We don't know specifically what it is. But it's not anything fundamentally mysterious. It's a particle. Dark energy is a different story. So dark energy is indeed uniformly spread throughout space and has this very weird property that it doesn't seem to evolve as far as we can tell. It's the same amount of energy in every cubic centimeter of space from moment to moment in time. That's why far and away the leading candidate for dark energy is Einstein's cosmological constant. The cosmological constant is strictly constant, 100% constant. The data say it had better be 98% constant or better. So 100% constant works, right? And it's also very robust. It's just there. It's not doing anything. It doesn't interact with any other particles. It makes perfect sense. Probably the dark energy is the cosmological constant. The dark matter, super important to emphasize here. It was hypothesized at first in the 70s and 80s, mostly to explain the rotation of galaxies. Today, the evidence for dark matter is both much better than it was in the 1980s and from different sources. It is mostly from observations of the cosmic background radiation or of large-scale structure. So we have multiple independent lines of evidence, also gravitational lensing and things like that, many, many pieces of evidence that say that dark matter is there. And also that say that the effects of dark matter are different than if we modified gravity. So that was my first answer to your question is dark matter, we have a lot of evidence for. But the other one is, of course, we would love it if it weren't dark matter. Our vested interest is 100% aligned with it being something more cool and interesting than dark matter, because dark matter is just a particle. That's the most boring thing in the world.
And it's non-uniformly distributed through space, dark matter?
Absolutely, yeah.
And so
you can even see maps of it that we've constructed from gravitational lensing.
So verifiable sort of clumps of dark matter in the galaxy that explain stuff.
Bigger than the galaxy, sadly. Like, we think that in the galaxy, dark matter is lumpy, but it's weaker. Its effects are weaker. But on the scale of large-scale structure and clusters of galaxies and things like that, yes, we can show you where the dark matter is.
Could there be a super cool explanation for dark matter that would be interesting as opposed to just another particle that sits there in clumps?
The super cool explanation would be modifying gravity rather than inventing a new particle. Oh. Sadly, that doesn't really work. We've tried. I've tried. That's my third paper that was very successful. I tried to unify dark matter and dark energy together. That was my idea. That was my aspiration, not even idea. I tried to do it. It failed even before we wrote the paper. I realized that my idea did not help. It could possibly explain away the dark energy, but it would not explain away the dark matter. And so I thought it was not that interesting, actually. And then two different collaborators of mine said, has anyone thought of this idea? Like, they had thought of exactly the same idea completely independently of me. I said, well, if three different people found the same idea, maybe it is interesting. And so we wrote the paper. And yeah, it was very interesting. People are very interested in it.
Can you describe this paper a little bit? Like, it's just, It's fascinating how much of a thing there is, dark energy and dark matter, and we don't quite understand it. So, what was your dive into the exploring how to unify the two?
So here is what we know about dark matter and dark energy. They become important in regimes where gravity is very, very, very weak. That's kind of the opposite from what you would expect if you actually were modifying gravity. Like there's a rule of thumb in quantum field theory, et cetera, that new effects show up when the effects are strong, right? We understand weak fields, we don't understand strong fields. But okay, maybe this is different, right? So what do I mean by when gravity is weak? The dark energy shows up late in the history of the universe. Early in the history of the universe, the dark energy is irrelevant. But remember, the density of dark energy stays constant. The density of matter and radiation go down. So at early times, the dark energy was completely irrelevant compared to matter and radiation. At late times, it becomes important. That's also when the universe is dilute and gravity is relatively weak. Now think about galaxies, okay? A galaxy is more dense in the middle, less dense on the outside. And there's a phenomenological fact about galaxies that in the interior of galaxies, you don't need dark matter. That's not so surprising because the density of stars and gas is very high there, and the dark matter is just subdominant. But then there's generally a radius inside of which you don't need dark matter to fit the data, outside of which you do need dark matter to fit the data. So that's again when gravity is weak, right? So I asked myself, of course, we know in field theory, new effects should show up when fields are strong, not weak, but let's throw that out of the window. Can I write down a theory where gravity alters when it is weak? And we've already said what gravity is. What is gravity? It's the curvature of spacetime. So there are mathematical quantities that measure the curvature of spacetime. And generally, you would say, like, I have an understanding. Einstein's equation, which I explained to the readers in the book, relates the curvature of spacetime to matter and energy. The more matter and energy, the more curvature. So I'm saying, what if you add a new term in there that says the less matter and energy, the more curvature? No reason to do that, except to fit the data, right? So I tried to unify the need for dark matter and the need for dark energy.
That would be really cool if that was the case. Like
super cool, right? It'd be the best. It'd be great.
But
it didn't work.
It'd be really interesting if gravity did something funky when there's not much of it. Like almost like at the edges of it, it gets like noisy.
That was exactly the hope, right? But the great thing about physics is there are equations, right? I mean, you can come up with the words and you can wave your hands, but then you got to write down the equations, and I did. And I figured out that it could help with the dark energy, the acceleration of the universe. It doesn't help with dark matter at all. Yeah.
It just sucks that at the scale of galaxies and scale of solar systems, the physics is kind of boring.
Yeah, it does. I agree. Again, that's why it is a little bit, I tear my hair out when people who are not physicists accuse physicists, like you say, of sort of losing the plot because they need dark matter and dark energy. I don't want dark matter and dark energy. I want something much cooler than that. I've tried, but you got to listen to the equations and to the data.
You mentioned 3 papers. Your first awesome paper ever, and your second awesome paper ever. Of course, you wrote many papers, so you're being very harsh on the others. But
well, by the way, this is not awesomeness. This is impact.
Impact,
right?
Sure.
There's no correlation between awesomeness and impact.
Right.
Some of my best papers fell without a stone.
Tree falls in the forest.
Right? Yeah. The first paper was called Limits on a Lorentz and Parity Violating Modification of Electromagnetism or Electrodynamics. So we figured out how to violate Lorentz invariance, which is the symmetry underlying relativity. And the important thing is we figured out a way to do it that didn't violate anything else and was experimentally testable. So people love that. The second paper was called Quintessence and the Rest of the World. So quintessence is this dynamical dark energy field. The rest of the world is because I was talking about how the quintessence field would interact with other particles and fields and how to avoid the interactions you don't want. And the third paper was called Is Cosmic Speed Up Due to Gravitational Physics? Something like that. So you see the common theme. I'm taking, what we know, the standard model of particle physics, general relativity, tweaking them in some way, and then trying to fit the data.
And trying to make it so it's experimentally validated.
Ideally, yes, that's right. That's the goal.
You wrote the book Something Deeply Hidden on the Mysteries of Quantum Mechanics, and a new book coming out soon, part of that Biggest Ideas in the Universe series we mentioned, called Quanta and Fields. So that's focusing on quantum mechanics. Big question first. Biggest ideas in the universe. What to you is most beautiful or perhaps most mysterious about quantum mechanics?
Quantum mechanics is a harder one. I wrote a textbook on general relativity, and I started it by saying general relativity is the most beautiful physical theory ever invented. And I will stand by that. It is less fundamental than quantum mechanics, but quantum mechanics is a little more mysterious. So it's a little bit kludgy right now. If you think about how we teach quantum mechanics to our students, the Copenhagen interpretation, it's a god-awful mess. Like, no one's going to accuse that of being very beautiful. I'm a fan of the many worlds interpretation of quantum mechanics, and that is very beautiful in the sense that fewer ingredients, just one equation, and it could cover everything in the world. It depends what you mean by beauty, but I think that the answer to your question is quantum mechanics can start with extraordinarily austere, tiny ingredients, and in principle lead to the world, right? That boggles my mind. It's much more comprehensive. General relativity is about gravity, and that's great. Quantum mechanics is about everything and seems to be up to the task. And so I don't know, is that beauty or not, but it's certainly impressive.
So both for the theory, the predictive power of the theory, and the fact that the theory describes tiny things creating everything we see around us.
It's a monist theory. In classical mechanics, I have a particle here, a particle there. I describe them separately. I can tell you what this particle is doing, what that particle is doing. In quantum mechanics, we have entanglement, right? As Einstein pointed out to us in 1935. And what that means is there is a single state for these two particles. There's not one state for this particle, one state for the other particle. And indeed, there's a single state for the whole universe, called the wave function of the universe, if you want to call it that. And it obeys one equation. And it is our job then to sort of chop it up, to carve it up, to figure out how to get tables and chairs and things like that out of it.
You mentioned the many worlds interpretation, and it is, in fact, beautiful. But it's one of your more controversial things you stand behind.
Yeah.
You've probably gotten a bunch of flack for it.
I'm a big boy. I can take it.
Well, can you first explain it and then maybe speak to the flack you may have gotten?
Sure. The classic experiment to explain quantum mechanics to people is called the Stern-Gerlach experiment. You're measuring the spin of a particle, okay? And in quantum mechanics, the spin is just a spin. It's the rate at which something is rotating around in a very down-to-earth sense. The difference being is that it's quantized. So for something like a single electron or a single neutron, it's either spinning clockwise or counterclockwise. Those are the only two, let's put it this way, those are the only two measurement outcomes you will ever get. There's no it's spinning faster or slower. It's either spinning one direction or the other. That's it. Two choices, okay? According to the rules of quantum mechanics, I can set up an electron, let's say, in a state where it is neither purely clockwise or counterclockwise, but a superposition of both. And that's not just because we don't know the answer. It's because it truly is both until we measure it. And then when we measure it, we see one or the other. So this is the fundamental mystery of quantum mechanics, is that how we describe the system when we're not looking at it is different from what we see when we look at it. So what we teach our students in the Copenhagen way of thinking is that the act of measuring the spin of the electron causes a radical change in the physical state. It spontaneously collapses from being a superposition of clockwise and counterclockwise to being one or the other. And you can tell me the probability that that happens, but that's all you can tell me. And I can't be very specific about when it happens, what caused it to happen, why it's happening, none of that. That's all called the measurement problem of quantum mechanics. So many worlds just says, look, I just told you a minute ago that there's only one wave function for the whole universe. And that means that you can't take too seriously just describing the electron. You have to include everything else in the universe. In particular, you clearly have to interact with the electron in order to measure it. So whatever is interacting with the electron should be included in the wave function that you're describing. And look, maybe it's just you. Maybe your eyeballs are able to perceive it, but okay, I'm going to include you in the wave function. And if you do that, let's be, since you have a very sophisticated listenership, I'll be a little bit more careful than average. What does it mean to measure the spin of the electron? We don't need to go into details, but we want the following thing to be true. If the electron were in a state that was 100% spinning clockwise, then we want the measurement to tell us it was spinning clockwise. We want your brain to go, yes, the electron was spinning clockwise, right? Likewise, if it was 100% counterclockwise, we want to see that, to measure that. The rules of quantum mechanics, the Schrodinger equation of quantum mechanics, is 100% clear that if you want to measure it clockwise when it's clockwise and measure it counterclockwise when it's counterclockwise, then when it starts out in a superposition, what will happen is that you and the electron will entangle with each other. And by that, I mean that the state of the universe evolves into part saying the electron was spinning clockwise and I saw it clockwise. And part of the state is it's in a superposition with the part that says the electron was spinning counterclockwise and I saw it counterclockwise. Everyone agrees with this. Entirely uncontroversial, straightforward consequence of the Schrodinger equation. And then Niels Bohr would say, and then part of that wave function disappears. And we're in the other part. And you can't predict which part it will be, only the probability. Hugh Everett, who was a graduate student in the 1950s, was thinking about this, says, I have a better idea. Part of the wave function does not magically disappear. It stays there. The reason why that idea, Everett's idea, that the whole wave function always sticks around and just obeys the Schrodinger equation, was not thought of years before, is because naively you look at it and you go, okay, this is predicting that I will be in a superposition, that I will be in a superposition of having seen the electron be clockwise and having seen it be counterclockwise. No experimenter has ever felt like they were in a superposition. You always see an outcome, okay? Everett's move, which was kind of genius, was to say, the problem is not the Schrodinger equation. The problem is you have misidentified yourself in the Schrodinger equation. You have said, oh, look, there's a person who saw counterclockwise. There's a person who saw clockwise. I should be that superposition of both. And Everett says, no, you're not. Because the part of the wave function in which the spin was clockwise, once that exists, it is completely unaffected by the part of the wave function that says the spin was counterclockwise. They are apart from each other. They are uninteracting. They have no influence. What happens in one part has no influence in the other part. So Everett says the simple resolution is to identify yourself as either the one who saw spin clockwise or the one who saw spin counterclockwise. There are now two people. Once you've done that experiment, the Schrodinger equation doesn't have to be messed with. All you have to do is locate yourself correctly in the wave function. That's many worlds.
The number of worlds is
very big.
Very, very, very big. Where do those worlds fit? Where do they go?
The short answer is the worlds don't exist in space. Space exists separately in each world. So, I mean, there's a technical answer to your question, which is Hilbert space, the space of all possible quantum mechanical states. But physically, we want to put these worlds somewhere. That's just a wrong intuition that we have. There is no such thing as the physical spatial location of the worlds because space is inside the worlds.
One of the properties of this interpretation is that you can't travel from one world to the other.
That's right.
Which kind of makes you feel that they're existing separately.
They are existing separately and simultaneously.
Without
locations in space.
How is it possible to visualize them existing without a location in space?
The real answer to that, the honest answer, is the equations predict it.
Yeah.
If you can't visualize it, So much worse for you. The equations are crystal clear about what they're predicting.
Is there a way to get to the closer to understanding and visualizing the weirdness of the implications of this?
I don't think it's that hard. It wasn't that hard for me. I don't mind the idea that when I make a quantum mechanical measurement, there is later on in the universe multiple descendants of my present self who got different answers for that measurement. I can't interact with them. Hilbert space, the space of all quantum wave functions, was always big enough to include all of them. I'm going to worry about the parts of the universe I can observe. So let's put it this way. Many worlds comes about by taking the Schrodinger equation seriously. The Schrodinger equation was invented to fit the data, to fit the spectrum of different atoms and different, emission and absorption experiments. And it's perfectly legitimate to say, well, okay, you're taking the Schrodinger equation, you're extrapolating it, you're trusting it, believing it beyond what we can observe. I don't want to do that, right? That's perfectly legit, except, okay, then what do you believe? Come up with a better theory. You're saying you don't believe the Schrodinger equation. Tell me the equation that you believe in. Turns out, and people have done that, turns out it's super hard to do that in a legitimate way that fits the data.
And many worlds is a really clean.
Absolutely. The most austere, clean, no extra baggage theory of quantum mechanics.
But if it in fact is correct, isn't this the weirdest thing of anything we know?
Yes. In fact, let me put it this way. The single best reason, in my mind, to be skeptical about many worlds is not because it doesn't make sense or it doesn't fit the data or I don't know where the worlds are going or whatever. It's because to make that extrapolation, to take seriously the equation that we know is correct in other regimes, requires new philosophy, requires a new way of thinking about identity, about probability, about prediction, a whole bunch of things. It's work to do that philosophy, and I've been doing it, and others have done it, and I think it's very, very doable, but it's not straightforward. It's not a simple extrapolation from what we already know. It's a grand extrapolation very far away. And if you just wanted to be sort of methodologically conservative and say, that's a step too far, I don't want to buy it, I'm sympathetic to that. I think that you're just wimping out. I think that you should have more courage, but I get the impulse.
And there is, under many worlds, an era of time where if you rewind it back, there's going to be one initial state.
That's right. All of quantum mechanics, all different versions require a kind of arrow of time. It might be different in every kind, but the quantum measurement process is irreversible. You can measure something, it collapses, you can't go backwards. If someone tells you the outcome, if I say, I've measured an electron, its spin is clockwise, and they say, what was it before I measured it? You know there was some part of it that was clockwise, but you don't know how much, right? And many worlds is no different. But the nice thing is that the kind of arrow of time you need in many worlds is exactly the kind of arrow of time you need anyway for entropy and thermodynamics and so forth. You need a simple, low entropy initial state. That's what you need in both cases.
So if you actually look at, under many worlds, into the entire history of the universe, correct me if I'm wrong, but it looks very deterministic.
Yes.
In each moment, does the moment contain the memory of the entire history of the universe? To you, does the moment contain the memory of everything that preceded it?
As far as we know, so according to many worlds, the wave function of the universe, all the branches of the universe at once, all the worlds, does contain all the information. Calling it a memory is a little bit dangerous because it's not the same kind of memory that you and I have in our brains, because our memories rely on the arrow of time. And the whole point of the Schrodinger equation or Newton's laws is they don't have an arrow of time built in. They're reversible. The state of the universe not only remembers where it came from, but also determines where it's going to go in a way that our memories don't do that.
But our memories, we can do replay. Can you do this?
We can, but the act of forming a memory increases the entropy of the universe. It is an irreversible process also, right? You can walk on a beach and leave your footprints there. That's a record of your passing. It will eventually be erased by the ever increasing entropy of the universe.
Well, but you can imperfectly replay it. I
Yeah.
guess, can we travel back in time imperfectly?
Oh, it depends on the level of precision you're trying to ask that question. You know, the universe contains the information about where the universe was, but you and I don't. We're nowhere close.
And it's what computationally very costly to try to consult the universe.
Well, it depends on, again, exactly what you're asking. Like, there are some simple questions, like what was the temperature of the universe 30 seconds after the Big Bang? We can answer that, right? That's kind of amazing that we can answer that to pretty high precision. But if you want to know where every atom was, then no.
What to you is the Big Bang? Why did it happen?
We have
What
no idea.
what
I think that's a super important question that I can imagine making progress on. But right now, I'm more or less maximally uncertain about what the answer
you
is.
think black holes will help?
No,
Potentially?
not
No.
that much. Quantum gravity will help, and maybe black holes will help us figure out quantum gravity. So indirectly, yes. But we have the situation where general relativity, Einstein's theory, unambiguously predicts there was a singularity in the past. There was a moment of time when the universe had infinite curvature, infinite energy, infinite expansion rate, the whole bit. That's just a fancy way of saying the theory has broken down. And classical general relativity is not up to the task of saying what really happened at that moment. So it is completely possible there was, in some sense, a moment of time before which there were no other moments. And that would be the Big Bang. Even if it's not a classical general relativity kind of thing, even if quantum mechanics is involved, maybe that's what happened. It's also completely possible there was time before that, space and time, and they evolved into our hot Big Bang by some procedure that we don't really understand.
And if time and space are emergent, then the before even starts getting real weird.
Well, I think that if there is a first moment of time, that would be very good evidence, or that would fit hand in glove with the idea that time is emergent. If time is fundamental, then it tends to go forever because it's fundamental.
Well, yeah. I mean, the general formulation of this question is what's outside of it? Well, what's outside of our universe? So in time and in space. I know it's a pothead question, Sean. I understand. I apologize.
Look, that's my life. My life is asking pothead questions.
Okay.
Some of them, the answer is that's not the right way to think about it.
Okay. But is it possible to think at all about what's outside our universe?
It's absolutely legit to ask questions, but you have to be comfortable with the possibility that the answer is there's no such thing as outside our universe. That's absolutely on the table. In fact, that is the simplest, most likely to be correct answer that we know of.
But it's the only thing in the universe that wouldn't have an outside.
If the universe is the totality of everything, it would not have an outside.
That's so weird to think that there's not an outside. We want there to be. We want there to be sort of a creative force that led to this, and an outside, like this is our town, and then there's a bigger world, and there's always a bigger world, and
because that is our experience. That's the world we grew up in, right? The universe doesn't need to obey those rules.
Such a weird thing.
When I was a kid, that used to keep me up at night. Like, what if the universe had not existed?
Right. And it feels like a lot of pressure that if this is the only universe, and we're here, one of the few intelligent civilizations, maybe the only one. It's the old theories that we're the center of everything. You just feel suspicious. That's why many worlds is kind of exciting to me, because it is humbling in all the right kinds of ways. It feels like infinity is the way this whole thing runs.
There's one pitfall that I'll just mention, because there's a move that is made in these theoretical edges of cosmology that I think is a little bit mistaken, which is to say, I'm going to think about the universe on the basis of imagining that I am a typical observer. This is called the principle of typicality or the principle of mediocrity or even the Copernican principle. Nothing special about me. I'm just typical in the universe. But then you draw some conclusions from this. And what you end up realizing is you've been hilariously presumptuous because by saying I'm a typical observer in the universe, you're saying typical observers in the universe are like me. And that is completely unjustified by anything. So I'm not telling you what the right way to do it is, but these kinds of questions that are not quite grounded in experimental verification or falsification are ones you have to be very careful about.
That to me is one of the most interesting questions. There's different ways to approach it, but like, what's outside of this? How did the Big Bang start? How do we get something from nothing? That's always the thing you're sneaking up to. When you're studying all of these questions, you're always sneaking. That's where the black hole and the unifying, getting quantum gravity, all this kind of stuff. You're always sneaking up to that question. Where did all of this come from? So, and I think that's probably an answerable question, right?
No,
it doesn't have to be. So you think there could be a turtle at the bottom of this that refuses to reveal its identity?
Yes. I think that specifically the question, why is there something rather than nothing?
Yeah.
Does not have the kind of answer that we would ordinarily attribute to why questions. Because typical why questions are embedded in the universe. And when we answer them, we take advantage of the features of the universe that we know and love. But the universe itself, as far as we know, is not embedded in anything bigger or stronger, and therefore it can just be.
Do you think it's possible this whole place is simulated?
Sure.
It's a really interesting, dark, twisted video game that we're all existing in.
You know, my own podcast listeners, Mindscape listeners, tease me because they know from my AMA episodes that if you ever start a question by asking, do you think it's possible that? The answer is going to be yes. That might not be the answer that you care about, but it's possible, sure, as long as you're not, adding two even numbers together and getting an odd number.
When you say it's possible, there's a mathematical yes, and then there's more of like intuitive.
Yeah. You want to know whether it's plausible. You want to know, is there a reasonable non-zero credence to attach to this? I don't think that there's any philosophical knockout objection to the simulation hypothesis. I also think that there's absolutely no reason to take it seriously.
Do you think humans will try to create one? I guess that's how I always think about it. I see what I've spent quite a bit of time over the past few years and a lot more recently in virtual worlds, and just am always captivated by the possibility of creating higher and higher resolution worlds. And as we'll talk a little bit about artificial intelligence, sort of the advancement on the Sora front, you can automatically generate those worlds, and the possibility of existing in those automatically generated worlds is pretty exciting, as long as there's a consistent physics, quantum mechanics, and general relativity that governs the generation of those worlds.
Yep.
So it just seems like humans will for sure try to create this.
Yeah, I think they will create better and better simulations. I think the philosopher David Chalmers has done what I consider to be a good job of arguing that we should treat things that happen in virtual reality and in simulated realities as just as real as the reality that we experience. I also think that as a practical matter, people will realize how much harder it is to simulate a realistic world than we naively believe. So this is not a my lifetime kind of worry.
Yeah, the practical matter of going from a sort of a prototype that's impressive to a thing that governs everything. Similar question on this front is in AGI. Yeah, you've said that we're very far away from AGI.
I want to eliminate the phrase AGI.
So basically, when you're analyzing large language models and seeing how far are they from whatever AGI is, and we can talk about different notions of intelligence, that we're not as close as kind of some people in public view are talking about. So what's your intuition behind that?
My intuition is basically that artificial intelligence is different than human intelligence. And so the mistake that is being made by focusing on AGI among those who do is an artificial agent, as we can make them now or in the near future, might be way better than human beings at some things, way worse than human beings at other things. And rather than trying to ask how close is it to being a human-like intelligence, we should appreciate it for what its capabilities are. And that will both be more accurate and help us put it to work and protect us from the dangers better, rather than always anthropomorphizing it.
I think the underlying idea there, under the definition of AGI, is that the capabilities are extremely impressive. That's not a precise statement,
Sure.
but
No, I
meaning,
get that. I completely agree.
and then the underlying question, where a lot of the debate is how impressive is it? What are the limits of large language models? Can they really do things like common sense reasoning? How much do they really understand about the world? Or are they just fancy mimicry machines?
Mm-hmm.
And so where do you fall on that as to the limits of large language models?
I don't think that there are many limits in principle. I'm a physicalist about consciousness and awareness and things like that. I see no obstacle to, in principle, building an artificial machine that is indistinguishable in thought and cognition from a human being. But we're not trying to do that, right? What a large language model is trying to do is to predict text. That's what it does. And it is leveraging the fact that we human beings, for very good evolutionary biology reasons, attribute intentionality and intelligence and agency to things that act like human beings. As I was driving here to get to this podcast space, I was using Google Maps, and Google Maps was talking to me, but I wanted to stop to get a cup of coffee. So I didn't do what Google Maps told me to do. I went around a block that it didn't like. And so it gets annoyed, right? It says like, no, why are you doing it? It doesn't say exactly in this, but you know what I mean. It's like, no, turn left, and you turn right. It is impossible as a human being not to feel a little bit sad that Google Maps is getting mad at you. It's not even trying to. It's not a large language model. It's not, no aspirations to intentionality, but we attribute that all the time. Dan Dennett, the philosopher, wrote a very influential paper on the intentional stance. The fact that it's the most natural thing in the world for we human beings to attribute more intentionality to artificial things than are really there, which is not to say it can't be really there. But if you're trying to be rational and clear thinking about this, the first step is to recognize our huge bias towards attributing things below the surface to systems that are able to, at the surface level, act human.
So if that huge bias of intentionality is there in the data, in the human data, in the vast landscape of human data that AI models, large language models, and video models in the future are trained on, don't you think that intentionality will emerge as fundamental to the behavior of these systems naturally?
I don't think it will happen naturally. I think it could happen. Again, I'm not against the principle, but again, the way that large language models came to be and what they're optimized for is wildly different than the way that human beings came to be and what they're optimized for. So I think we're missing a chance to be much more clear-headed about what large language models are by judging them against human beings, again, both in positive ways and negative ways.
Well, I think sort of to push back on what they're optimized for is different to describe how they're trained versus what they're optimized for. So they're trained in this very trivial way of predicting text tokens.
Mm-hmm.
But you can describe what they're optimized for, and what the actual task in hand is to construct a world model, meaning an understanding of the world. And that's where it starts getting closer to what humans are kind of doing. We're just, in the case of large language models, know how the sausage is made, and we don't know how it's made for us humans.
But they're not optimized for that. They're optimized to sound human.
That's the fine tuning. But the actual training is optimized for understanding, creating a compressed representation of all the stuff that humans have created on the internet. And the hope is that gives you a deep understanding of the world.
Yeah. So that's why I think that there's a set of hugely interesting questions to be asked about the ways in which large language models actually do represent the world. Because what is clear is that they're very good at acting human. The open question in my mind is the easiest, most efficient, best way to act human to do the same things that human beings do? Or are there other ways? And I think that's an open question. I just heard a talk by Melanie Mitchell at Santa Fe Institute, an artificial intelligence researcher. And she told two stories about two different papers, one that someone else wrote and one that her group is following up on. And they were modeling Othello. Othello, the game with a little rectangular board, white and black squares. So the experiment was the following. They fed a neural network the moves that were being made in the most symbolic form, like E5 just means that, okay, you put a token down E5. So it gives a long string. It does this for millions of games, right? Real legitimate games. And then it asks the question, the paper asks the question, okay, you've trained it to tell what would be a legitimate next move from not a legitimate next move. Did it in its brain, in its little large language model brain, I don't even know if it's technically a large language model, but a deep learning network, did it come up with a representation of the Othello board? Well, how do you know? And so they construct a little probe network that they insert and you ask it, what is it doing right at this moment, right? And the answer is that the little probe network can ask, would this be legitimate, or is this token white or black or whatever? Things that in practice would amount to it's invented the Othello board. And it found that the probe got the right answer, not 100% of the time, but more than by chance, substantially more than by chance. So they said there's some tentative evidence that this neural network has discovered the Othello board just out of data, raw data, right? But then Melanie's group asked the question, okay, are you sure that that understanding of the Othello board wasn't built into your probe? And what they found was like at least half of the improvement was built into the probe, not all of it, right? And look, a Othello board is way simpler than the world. So that's why I just think it's an open question whether or not it would be remarkable either way to learn that large language models that are good at doing what we train them to do are good because they've built the same kind of model of the world that we have in our minds, or that they're good despite not having that model. Either one of these is an amazing thing. I just don't think the data are clear on which one is true.
I think I have some sort of intellectual humility about the whole thing because I was humbled by several stages in the machine learning development over the past 20 years. And I would never have predicted that LLMs, the way they're trained, on the scale of data they're trained, would be as impressive as they are.
Mm-hmm.
And that's where intellectual humility steps in, where my intuition would say something like with Melanie, where you need to be able to have very sort of concrete common sense reasoning, symbolic reasoning type things in a system in order for it to be very intelligent. But here, I'm so impressed by what it's capable to do trained on next token prediction, essentially. That's my conception of the nature of intelligence is just completely, not completely, but humbled, I should say.
Look, and I think that's perfectly fair. I also I will say pleasantly, I don't know whether it's pleasantly or unpleasantly, but factually surprised by the recent rate of progress. Clearly, some kind of phase transition percolation has happened, right? And the improvement has been remarkable, absolutely amazing. That I have no arguments with. That doesn't yet tell me the mechanism by which that improvement happened. Constructing a model much like a human being would have is clearly one possible mechanism, but part of the intellectual humility is to say maybe there are others.
I was chatting with the CEO of Anthropic, Dario Amodei, so behind Claude, and that company, but a lot of the AI companies are really focused on expanding the scale of compute. Sort of, if we assume that AI is not data limited, but is compute limited, you can make the system much more intelligent by using more compute. So let me ask you almost on the physics level, do you think physics can help expand the scale of compute and maybe the scale of energy required to make that compute happen?
Yeah, 100%. I think this is like one of the biggest things that physics can help with, and it's an obvious kind of low-hanging fruit situation where uh, the heat generation, the inefficiency, the waste of existing high-level computers is nowhere near the efficiency of our brains. It's hilariously worse. And we kind of haven't tried to optimize that hard on that frontier. I mean, your laptop heats up when you're sitting on your lap, right? It doesn't need to. Your brain doesn't heat up like that. So clearly, there exists in the world of physics the capability of doing these computations with much less waste heat being generated. And I look forward to people doing that. Yeah.
Are you excited for the possibility of nuclear fusion?
I am cautiously optimistic. Excited to be too strong. I mean, it'd be great, right? But if we really tried solar power, it would also be great.
I think Elias Discover said this, that the future of humanity on Earth will be the entire surface of Earth is covered in solar panels and data centers.
Why would you waste the surface of the Earth with solar panels? Put them in space.
Sure, you can go in space. Yeah,
Space is bigger than the Earth.
yeah, just solar panels everywhere.
Yeah.
Just I like it.
We already have fusion. It's called the sun.
Yeah, that's true. And there's probably more and more efficient ways of catching that energy.
Sending it down is the hard part. Absolutely. But
Yeah.
that's an engineering problem. Yeah.
So I just wonder where the data centers, the compute centers can expand to, if that's the future. If AI is as effective as as it possibly could be, then the scale of computation will keep increasing. And perhaps it's a race between efficiency and scale.
There are constraints, right? You know, there's a certain amount of energy, a certain amount of damage we can do to the environment before it is not worth it anymore. So, yeah, I think that's a new question. In fact, it's kind of frustrating because we get better and better at doing things efficiently, but we invent more things we want to do faster than we get good at doing them efficiently. So, we're continuing to make things worse in various ways.
I mean, that's the dance of humanity. We're constantly creating better and better technologies that are potentially causing a lot more harm, and that includes for weapons. It includes AI used as weapons. That includes nuclear weapons, of course. Which is surprising to me that we haven't destroyed human civilization yet, given how many nuclear warheads are out there.
Look, I'm with you. Between nuclear and bioweapons, it is a little bit surprising that we haven't caused enormous devastation. Of course, we did drop 2 atomic bombs on Japan, but compared to what could have happened or could happen tomorrow, it could be much worse. Yeah.
It does seem like there's a underlying. Speaking of quantum fields, there's like a field of goodness within the human heart that, like, in some kind of game theoretic way, we create really powerful things that could destroy each other. And there's greed and ego and all this kind of power hungry dictators that are at play here in all the geopolitical landscape. But we somehow always don't go too far.
Yeah, but that's exactly what you would say right before we went too far.
Right before we went too far. And that's why we don't see aliens. So you're, like I mentioned, associated with Santa Fe Institute. I just would love to take a stroll down the landscape of ideas explored there.
Sure.
So they look at complexity in all kinds of ways. What do you think about the emergence of complexity from simple things interacting simply?
I think it's a fascinating topic. I mean, that's why I'm thinking about these things these days rather than the papers that I was describing to you before. All of those papers I described to you before are guesses. Like, what if the laws of physics are different in the following way? And then you can work out the consequences. At some point in my life, I said, like, what is the chance I'm going to guess right? Einstein guessed right, Steven Weinberg guessed right, but there's a very small number of times that people guessed right. Whereas with this emergence of complexity from simplicity, I really do think that we haven't understood the basics yet. I think we're still kind of pre-paradigmatic. There have been some spectacular discoveries. People like Jeffrey West at Santa Fe and others have really given us true insights into important systems, but still there's a lot of the basics I think are not understood. And so searching for the general principles is what I like to do. And I think it's absolutely possible that, I mean, to be a little bit more substantive than that, I think this is kind of a cliche. I think the key is information. And I think that what we see through the history of the universe as you go from simple to more and more complex is really subsystems of the universe figuring out how to use information to do whatever, to survive or to thrive or to reproduce. I mean, that's the sort of fuel, the leverage, the resource that we have for a while anyway, until the heat death. But that's where the complexity is really driven by.
Yeah, but the mechanism of it, what I mean, you mentioned Jeffrey West. What are interesting inklings of progress in this realm, and what are systems that interest you in terms of information? So, I mean, for me, just as a fan of complexity, just even looking at simple cellular automata is always just a fascinating way to illustrate the emergence of complexity.
So for those of the listeners who don't know, viewers, cellular automata come from imagining a very simple configuration. For example, a set of ones and zeros along a line. And then you invent a rule that says, okay, I'm going to evolve this in time. And generally, the simplest ones start with just each block of 3 ones and zeros have a rule that they will deterministically go to either a 1 or a 0. And you can actually classify all the different possibilities, a small number of possible cellular automata of that form. And what was discovered by various people, including Stephen Wolfram, is some of these cellular automata have the feature that you start from almost nothing, like 0, 0, 0, 0, 1, 0, 0, 0, 0, and you let it rip, and it becomes wildly complex. Okay? So this is very provocative, very interesting. It's also not how physics works at all. Because as we said, physics conserves information. You can go forward or backwards. These cellular automata do not. They're not reversible in any sense. You've built in an arrow of time. You have a starting point, and then you evolve. So what I'm interested in is seeing how in the real world, with the real laws of physics and underlying reversibility, but macroscopic irreversibility from entropy in the arrow of time, et cetera, how does that lead to complexity? I think that that's an answerable question. I don't think that cellular automata are really helping us in that one.
So, what is in that? What does the landscape of entropy in the universe look like? Sean?
Well, entropy is hard to localize. It's a property of systems, not of parts of systems, right? Having said that, we can do approximate answers to the question. The answer is black holes are huge in entropy. Let's put it this way. The whole observable universe that we're in had a certain amount of entropy before stars and planets and black holes started to form. 10 to the 88th. I can even tell you the number, okay? The single black hole at the center of our galaxy has entropy, 10 to the 90. The single black hole at the center of our galaxy has more entropy than the whole universe used to have not too long ago. So most of the entropy in the universe today is in the form of black holes.
Okay, that's fascinating, first of all. But second of all, if we take black holes away, what are the different interesting perturbations in entropy across space? Where do we Earthlings fit into that?
The interesting thing to me is that if you start with a system that is isolated from the rest of the universe, and you start it at low entropy, there's almost a theorem that says if you're very, very, very low entropy, then the system looks pretty simple. Because there's low entropy means there's only a small number of ways that you can rearrange the parts to look like that. So if there's not that many ways, the answer is going to look simple. But there's also almost a theorem that says when you're at maximum entropy, the system is going to look simple because it's all smeared out. If it had like interesting structure, then it would be complicated, right? So entropy in this isolated system only goes up. That's the second law of thermodynamics. But complexity starts low, goes up, and then goes down again. Sometimes people mistakenly think that complexity or life or whatever is fighting against the second law of thermodynamics, fighting against the increase of entropy. That is precisely the wrong way to think about it. We are surfers riding the wave of increasing entropy. We rely on increasing entropy to survive. That is part of what makes us special. This table maintains its stability mechanically, by which I mean there's molecules, they have forces on each other, and it holds up. You and I aren't like that. We maintain our stability dynamically by ingesting food, fuel, right? Food and water and air and so forth, burning it, increasing its entropy. We are non equilibrium, quasi steady state systems. We are using the fuel the universe gives us in the form of low entropy energy to maintain our stability.
I just wonder what that mechanism of surfing looks like. I mean, that's where, first of all, I mean, one question to ask: do you think it's possible to have a kind of science of complexity where you have very precise ways or clearly defined ways of measuring complexity?
I think it is, and I think we don't. It's possible to have it. I don't think we yet have it. Because, in part because complexity is not a univalent thing. There's different ideas that go under the rubric of complexity. One version is just Kolmogorov complexity, right? If you have a configuration or a string of numbers or whatever, can you compress it so that you have a small program that will output that? That's Kolmogorov complexity. But that's the complexity of a string of numbers, okay? It's not like the complexity of a problem, right? Computational complexity, the traveling salesman problem, or factoring large numbers. That's a whole different kind of question that is also about complexity. So we don't have a sort of unified view of it.
So you think it's possible to have a complexity of a physical system
Yeah,
in the same
absolutely.
way we do entropy?
Yeah.
You think that's a Sean Carroll paper or what?
We're working on various things. The glib thing that I'm trying to work on right now with a student is complexogenesis. How does complexity come to be if all the universe is doing is moving from low entropy to high entropy?
It's a sexy name.
It's a good name. Yeah, I like the name.
Oh,
Now he's
you
got to
know,
write the paper.
Sometimes a name
Yeah.
arose by any other name. In which context the birth of complexity are you most interested in?
Well, I think it comes in stages, right? So I think that if you go from I'm again a physicist, so biologists studying evolution will talk about how complexity evolves all the time, the complexity of the genome, the complexity of our physiology, right? But they take for granted that life already existed, and entropy is increasing and so forth. I want to go back to the beginning and say the early universe was simple and low entropy, and entropy increases with time, and the universe sort of differentiates and becomes more complex. But that statement, which is indisputably true, has different meanings because complexity has different meanings. So sort of the most basic primal version of complexity is what you might think of as configurational complexity. That's what Kolmogorov gets at. How much information do you need to specify the configuration of the system? Then there's a whole other step where subsystems of the universe start burning fuel, right? So in many ways, a planet and a star are not that different in configurational complexity. They're both spheres with density high at the middle and getting less as you go out. But there's something fundamentally different because the star only survives as long as it has fuel, right? I mean, then it turns into a brown dwarf or a white dwarf or whatever. But as a star, as a main sequence star, it is an out of equilibrium system, but it's more or less static, right? Like if I spill the coffee mug and it falls, in the process of falling, it's out of equilibrium, but it's also changing all the time. A specific kind of system is where it looks sort of macroscopically stationary, like a star, but underneath the hood, it's burning fuel to beat the band in order to maintain that stability. So as stars form, that's a different kind of complexity that comes to be. Then there's another kind of complexity that comes to be, roughly speaking, at the origin of life, because that's where you have information really being gathered and utilized by subsystems of the universe. And then arguably, there's any number of stages past that. I mean, one of the most obvious ones to me is we talk about simulation theory, but you and I run simulations in our heads. They're just not that good, but we imagine different hypothetical futures, right? Bacteria don't do that. So that's the kind of information processing that is a form of complexity. And so I would like to understand all these stages and how they fit together.
Yeah, imagination.
Yeah. Mental time travel.
Yeah, the things going on in my head when I'm imagining worlds are super compressed representations of those worlds, but I get to the essence of them. And maybe it's possible with non-human computing type devices to do those kinds of simulations in more and more compressed ways.
There's an argument to be made that literally what separates human beings from other species on Earth is our ability to imagine counterfactual hypothetical futures.
Yeah. I mean, that's one of the big features. I don't know if it's
Everyone has their own favorite little feature, but that's why I said there's an argument to be made. I did a podcast episode on it with Adam Bully. It developed slowly. I did a different podcast. Sorry to keep mentioning podcast episodes I did, but Malcolm McIver, who is an engineer at Northwestern, has a theory about one of the major stages in evolution is when fish first climbed onto land. And of course, that is a major stage of evolution, but in particular, there's a cognitive shift. Because when you're a fish swimming under the water, the attenuation length of light in water is not that long. You can't see kilometers away. You can see meters away. And you're moving at meters per second. So all of the evolutionary optimization is make all of your decisions on a time scale of less than a second. When you see something new, you have to make a rapid fire decision what to do about it. As soon as you climb onto land, you can essentially see forever, right? You can see stars in the sky. So now a whole new mode of reasoning opens up where you see something far away. And rather than saying, look up table, I see this, I react, you can say, okay, I see that thing. What if I did this? What if I did that? What if I did something different? And that's the birth of imagination eventually.
You've been critical on panpsychism.
Yes, you've noticed that, right?
Can you make the case for panpsychism and against it? So panpsychism is the idea that consciousness permeates all matter. It's maybe it's the fundamental force or a physics of the fabric of the universe.
Panpsychism, thought everywhere, consciousness everywhere, right?
It's to a point of entertainment. The idea frustrates you, which sort of as a fan is wonderful to watch. And you've had great episodes with panpsychists on your podcast where you go at it.
I had David Chalmers, who's one of the world's great philosophers, and he is panpsychism curious.
Yeah,
he doesn't commit to anything, but he's certainly willing to entertain it. Philip Goff, who I've had, who's a great guy, but he is devoted to panpsychism. Mm-hmm. In fact, he is almost single-handedly responsible for the upsurge of interest in panpsychism in the popular imagination. And the argument for it is supposed to be that there is something fundamentally uncapturable about conscious awareness by physical behavior of atoms and molecules. So the panpsychist will say, look, you can tell me maybe someday through advances of neuroscience and what have you, exactly what happens in your brain and how that translates into thought and speech and action. What you can't tell me is what it is like to be me. You can't tell me what I am experiencing when I see something that is red or that I taste something that is sweet. You can tell me what neurons fire, but you can't tell me what I'm experiencing. That first person inner subjective experience is simply not capturable by physics. And therefore, this is an old argument, of course, but then the therefore is supposed to be, I need something that is not contained within physics to account for that. And I'm just going to call it mind. We don't know what it is yet. We're going to call it mind, and it has to be separate from physics. And then there's two ways to go. If you buy that much, you can either say, okay, I'm going to be a dualist. I'm going to believe that there's matter and mind, and they are separate from each other, and they are interacting somehow. Or that's a little bit complicated and sketchy as far as physics is going to go. So I'm going to believe in mind, but I'm going to put it prior to matter. I'm going to believe that mind comes first and that consciousness is the fundamental aspect of reality, and everything else, including matter and physics, comes from it. That would be at least as simple as physics comes first, right? Now, the physicalist, such as myself, will say, I don't have any problem explaining what it's like to be you or what you experience when you see red. It's a certain way of talking about the atoms and the neurons, et cetera, that make up you. Just like the hardness or the brownness of this table, these are words that we attach to certain underlying configurations of ordinary physical matter, Likewise, sadness and redness or whatever are words that we attach to you to describe what you're doing. And when it comes to consciousness in general, I'm very quick to say I do not claim to have any special insight on how consciousness works, other than I see no reason to change the laws of physics to account for it.
If you don't have to change the laws of physics, where do you think it emerges from? Is consciousness an illusion? It's almost like a shorthand that we humans use to describe a certain kind of feeling we have when interacting with the world. Or is there some big leap that happens at some stage?
I almost never use the word illusion. Illusion means that there's something that you think you're perceiving that is actually not there. Like an oasis in the desert is an illusion. It has no causal efficacy. If you walk up to where the oasis is supposed to be, you'll say you were wrong about it being there. That's different than something being emergent or non-fundamental, but also real. Like this table is real, even though I know it's made of atoms. That doesn't remove the realness from the table. I think that consciousness and free will and things like that are just as real in tables and chairs.
Oasis in the desert does have causal efficacy in that you're
Incorrect
thirsty.
causal efficacy.
Well, you mean
It leads you to draw incorrect conclusions about the world.
Sure, but imagining a thing can sometimes bring it to reality, as we've seen, and that has a kind of a causal efficacy.
Sure, but your understanding of the world in a way that gives you power over it and influence over it is decreased rather than increased by believing in that oasis. That is not true about consciousness or this table.
You don't think you can increase the chance of a thing existing by imagining it existing?
Unless you build it or make it.
No, that's what I mean. Like imagining humans can fly. If you're
That's
the Wright
different than
brothers,
imagining that humans are flying.
right?
In terms of counterfactuals in the future, absolutely, imagination is crucially important. But that's not an illusion. That's just a
Okay. So it's
imagination.
the possibility of the future versus what reality is. I mean, the future is a concept, so you can time time is just a concept, so you can play with that. But yes, reality. So to you, so for example, I love asking this. So Donald Hoffman thinks that the entirety of the conversation we've been having about space-time is an illusion. Is it possible for you to steelman the case for that? Can you make the case for and against reality, as I think he writes, that the laws of physics as we know them with space-time is a kind of interface to a much deeper thing that we don't at all understand, and that we're fooling ourselves by constructing this world?
Well, I think there's like part of that idea that is perfectly respectable and part of it that is perfectly nonsensical. And I'm not even going to try to steelman the nonsensical part. The real part to me is what is called structural realism. So we don't know what the world is at a deep fundamental level, right? Let's put ourselves in the minds of people living 200 years ago. Like they didn't know about quantum mechanics, they didn't know about relativity. That doesn't mean they were wrong about the universe that they understood. They had Newton's laws, right? They could predict what time the sun was going to rise perfectly well. In the progress of science, the words that would be used to give the most fundamental description of how you were predicting the sun would rise changed, because now you have curved space-time and things like that, right? And you didn't have any of those words 200 years ago. But the prediction is the same. Why? Because that prediction, independent of what we thought the fundamental ontology was, the prediction pointed to something true about our understanding of reality. To call it an illusion is just wrong, I think. We might not know what the best, most comprehensive way of stating it is, but it's still true.
Is it true in the way, for example, belief in God is true? Because for most of human history, people have believed in a God or multiple gods, and that seemed very true to them as an explanation for the way the world is. Some of the deeper questions about life itself and the human condition and why certain things happen, that was a good explainer. So to you, that's not an illusion.
No, I think that was completely an illusion. I think it was a very, very reasonable illusion to be under. There are illusions. There are, substantive claims about the world that go beyond predictions that we can make and verify, which later turned out to be wrong. And the existence of God was one of them. If those people at that time had abandoned their belief in God and replaced it with a mechanistic universe, they would have done just as well at understanding things, right? Again, because there's so many things they didn't understand, it was very reasonable for them to have that belief. It wasn't that they were dummies or anything like that. But that is, as we understand the universe better and better, some things stick with us, some things get replaced.
So, like you said, you're a believer of the mechanistic universe. You're a naturalist, and as you've described, a poetic naturalist.
That's right.
What's the word poetic? What is naturalism, and what is poetic naturalism?
Naturalism is just the idea that all that exists is the natural world. There's no supernatural world. You can have arguments about what that means, but I would claim that the argument should be about what the word supernatural means, not the word natural. The natural world is the world that we learn about by doing science. The poetic part means that you shouldn't be too, I want to say, fundamentalist about what the natural world is. As we went from Newtonian space-time to Einsteinian space-time, something is maintained there. There is a different story that we can tell about the world. And that story in the Newtonian regime, if you want to fly a rocket to the moon, you don't use general relativity. You use Newtonian mechanics. That story works perfectly well. The poetic aspect of the story is that there are many ways of talking about the natural world. And as long as those ways latch on to something real and causally efficacious about the functioning of the world, then we attribute some reality and truth to them.
So the poetic really looks at the let's say the pothead questions at the edge of science. Is more open to them.
It's doing double duty a little bit, so that's why it's confusing. The more obvious, respectable duty it's doing is that tables are real. Even though you know that it's really a quantum field theory wave function, right? Tables are still real. They're a different way of talking about the underlying deeper reality of it. The other duty it's doing is that we move beyond purely descriptive vocabularies for discussing the universe onto normative and prescriptive and judgmental ways of talking about the universe. This painting is beautiful, that one is ugly. This action is morally right, that one is morally wrong. These are also ways of talking about the universe. They are not fixed by the phenomena. They are not determined by our observations. They cannot be ruled out by a crucial experiment. But they're still valid. They might not be universal. They might be subjective, but they're not arbitrary. And they do have a role in describing how the world works.
So you don't think it's possible to construct experiments that explore the realms of morality and even meaning? So those are subjective.
Yeah. They're human. They're personal.
But do you think that's just because we don't have the tools of science have not expanded enough to incorporate the human experience?
No, I don't think that's what it is. I think that what we mean by aesthetics or morality are we're attaching categories, properties to things that happen in the physical world. And there is always going to be some subjectivity to our attachment and how we do that. And that's okay. And the faster we recognize that and deal with it, the better off we'll be.
But if we deeply and fully understand the functioning of the human mind, won't be able to incorporate that?
No. That will absolutely be helpful in explaining why certain people have certain moral beliefs. It won't justify those beliefs as right or wrong.
Do you think it's possible to have a kind of general relativity, but that includes the observer effect where the human mind is the observer?
Sure.
So sort of like how we morph in the same way gravity morphs space-time, how does the human mind morph reality and have a very thorough theory of how that morphing actually happens?
That's a very pothead question, Lex, but that's
okay. But don't you think it's possible?
But the answer is yes. I think that there's right. I think that we're part of the physical world and the natural world. physicalism would have been just as good a word to use as naturalism, maybe even a more accurate word, but it's a little bit more off-putting. So I did want a snappier, more attractive label than physicalism.
Are there limits to science?
Sure, we just talked about one, right? Science can't tell you right from wrong. You need science to implement your ideas about right and wrong. If you are functioning on the basis of an incorrect view of how the world works, you might very well think you're doing right, but actually be doing wrong. But all the science in the world won't tell you which action is right and which action is wrong.
You know, dictators and people in power will sometimes use science as an authority to convince you what's right and wrong. Studying Nazi science is fascinating.
Yeah. But there's an instrumentalist view here. You have to first decide what your goals are, and then science can help you achieve those goals. If your goals are horrible, science has no problem helping you achieve them. Science is happy to help out.
Let me ask you about the method behind the madness on several aspects of your life. So you mentioned your approach to writing for research and writing popular books. How do you find the time of the day? Like, what's a day in the life of Sean Carroll looks like?
Very unclear how I find the time on.
So you don't have a thing where in the morning you're like you try to fight for 2 hours somewhere.
I don't. I'm really terrible at that. You know, my strategy for finding time is just to ignore interruptions and emails. But it's a different time every day. Some days it never happens. Some weeks it never happens.
You're able to pull it off because you're extremely prolific. So like you're able to have days where you don't write.
Oh my God!
And still write the next day.
Right.
Oh wow, that's a rare thing, right? A lot of prolific writers will carve out 2 hours because otherwise it just disappears.
Right. No, I get that. Yeah, I do. And yeah, it's just like everyone is, has their foibles or whatever. So I'm not able to do that. Therefore, I have to just figure it out on the fly.
And what's the actual process look like when you're writing popular stuff? You get behind a computer?
Yeah, get behind a computer. And my way of doing it, so my wife, Jennifer, is a science writer, but it's interesting because our techniques are entirely different. She will think about something, but then she will free write. She'll just sit at a computer and write. Like, I think this. And then that will be vastly compressed, edited, and rewritten or whatever until the final thing happens. I will just sit there silently thinking for a very long time, and then I will write what is almost the final draft. So a lot of it happens. There might be some scribbles for an outline or something like that, but a lot of it is in my brain before it's on the page.
So that's the case for the biggest ideas in the universe, the quanta book and the space-time motion book?
Yeah, Quanta and Fields, which is actually mostly about quantum field theory and particle physics. That's coming out in May, and that is I'm letting people in on things that no other book lets them in on. So I hope it's worth it. It's a challenge because there's a lot of equations.
I mean, you did the same thing with space-time motion. You did something quite interesting, which is like you made the equation the centerpiece of a book.
Right. There's a lot of equations. Book 2 is goes further in those directions than book 1 did. So it's more cool stuff. It's also more mind-bending. It's more of a challenge. Book 3 that I'm writing right now is called Complexity and Emergence.
Oh, wow.
And that'll be the final part of the trilogy.
Oh, that's fascinating. So there's a lot of probably ideas that are there. I mean, that's a real cutting edge.
Well, but I'm not trying to be cutting edge. In other words, I'm not trying to speculate in these books. Obviously, in other books, I've been very free about speculating, but the point of these books is to say things that 500 years from now will still be true. And so there are some things we know about complexity and emergence, and I want to focus on those. And I will mention, I'm happy to say, this is something that needs to be speculated about, but I won't pretend to be telling you what one is the right one.
You somehow found the balance between the rigor of mathematics and still accessible, which is interesting.
I try. I mean, look, these 3 books, the biggest ideas books, are absolutely an experiment. They're going to appeal to a smaller audience than other books will. But that audience should love them. Like my 16-year-old self would have been so happy to get these books. I can't tell you.
Yeah, in terms of looking back in history, those are books, the trilogy would be truly special in that way.
Worked for Lord of the Rings, so I figured, why not me?
You and Tolkien are just different styles, different topics.
Same ultimate reality.
Like we mentioned, Mindscape podcast. I love it. You interview a huge variety of experts from all kinds of fields. So, just several questions I want to ask. How do you prepare? How do you prepare to have a good conversation? How do you prepare in a way that satisfies, makes your own curious mind happy? All that kind of stuff.
Yeah, no, these are great questions, and I've sort of struggled and changed my techniques over the years. It's over 5-year-old podcast, it might be approaching 6 years old now. I started out over preparing when I first started. Like I had a journey that I was going to go down. Many of the people I talked to are academics or thinkers who write books, so they have a story to tell. I could just say, "Okay, give me your lecture," and then an hour later stop. Right. So the mistake is to sort of anticipate what the lecture would be and to ask the leading questions that would pull it out of them. What I do now is much more, here are the points, here are like the big questions that I'm interested in. And so I have a much sketchier outline to start and then try to make it more of a real conversation. I'm helped by the fact that it is not my day job. So I strictly limit myself to 1 day of my life per podcast episode on average. Some days take more. And that includes not just doing the research, but inviting the guest, recording it, editing it, publishing it. So I need to be very, very efficient at that. Yeah.
You enforce constraints for yourself in which creativity can emerge.
That's right. That's right. And, look, sometimes if I'm interviewing a theoretical physicist, I can just go in. And where interviewing an economist or a historian, I have to do a lot of work.
Do you ever find yourself getting lost in rabbit holes that serve no purpose except satisfying your own curiosity and then potentially expanding the range of things that can help your actual work and research and writing?
Yes, on both counts. I do. Some people have so many things to talk about that you don't know where to start or finish, right? Others have a message. And it's what's one of the things I discovered over the course of these years is the correlation with age. Like there are brilliant people, and I try very hard on the podcast to sort of get all sorts of people, right? Different ages and things like that. And bless their hearts, the most brilliant young people are not as practiced at wandering past their literal research, right? They have less mastery over the field as a whole, much less how to talk about it. Whereas certain older people just like have their pat answers, and that's kind of boring, right? So you want somewhere in between. The ideal person who has a broad enough of a scope that they can wander outside their specific papers they've written, but they're not overly practiced, so they're just giving you their canned answers.
I feel like there's like a connection to the metaphor of entropy and complexity, as you said, with the
edge of chaos. Yeah.
You also do incredible AMAs, and people should sign up to your Patreon, and because you can get to ask questions, Sean Carroll. Well, for several hours, you just answer in fascinating ways some really interesting questions. Is there something you could say about the process of finding the answers to those?
That's a great one. Again, it's evolved over time. So the Ask Me Anything episodes were first, when I started doing them, they were only for Patreon subscribers to both listen to and to ask the questions. But then I actually asked my Patreon subscribers, would you like me to release them publicly? And they overwhelmingly voted yes. So I do that. So the Patreon supporters ask the questions. Everyone can listen. And also at some point, I really used to try to answer every question, but now there's just too many. So I have to pick, and that's fraught with peril. And my personal standard for picking questions to answer is, what are the ones I think I have interesting answers to give for, right? So that both means if it's kind of the same old question about special relativity that I've gotten 100 times before, I'm not going to answer it, because you can just Google that. It's easier. There are some, very clear attempts to ask an interesting question that honestly just I don't have an answer to. Like, I read this science fiction novel. What do you think about it? I'm like, well, I haven't read it, so I can't help you there. What's your favorite color? I can tell you what it is, but it's not that interesting. And so I try to make it a mix. I try to it's not all physics questions, not all philosophy questions. I will talk about food or movies or politics or religion, if that's what people want to. I keep suggesting that people ask me for relationship advice, but they never do.
Yeah, I don't think I've heard. I don't think I've heard one.
Yeah, I'm willing to do it, but I'm a little reluctant because I don't actually like giving advice. But I do. But I'm happy to talk about those topics. I want to give several hours of talking, and I want to try to say things that I haven't said before and keep it interesting, keep it rolling. If you don't like this question, wait for the next one.
What are some of the harder questions you've gotten? Do you remember? What kinds of questions are difficult for you?
Rarely, but occasionally, people will ask me a super insightful philosophy question. Like, I hadn't thought of things in exactly that way. And I try to be, I try to recognize that a lot of times it's the opposite, where it's like, okay, you're clearly confused, and I'm going to try to explain how the question you should have asked.
Oh, I love those. Yeah, why that's the wrong question or that kind of stuff.
Right.
That's great.
Right.
That's great.
But the hard questions, I don't know. Like, I don't actually answer personal questions very much. Like, the most personal I will get are questions like, "What do you think of Baltimore?" Right? That much I can talk about. Or, "How are your cats doing?" Happy to talk about the cats in infinite detail. But very personal questions I don't get into.
But you even touch like politics and stuff like this.
Yeah, no, very happy to talk about politics. I try to be clear on, what is professional expertise, what is just me babbling, what is my level of credence in different things, where you're allowed to disagree, whether if you disagree, you're just wrong. And people can disagree with that also. But I do think, and I'm happy to go out on a limb a little bit. I'm happy to say, look, I don't know, but here's my guess, right? I just did a whole solo podcast, which was exactly that. And, it's interesting. Like, some people are like, oh, this was great. And there's a whole bunch of people like, why are you talking about this thing that you are not the world's expert in? So,
Well, I love the actual dance between humility and having a strong opinion on stuff, which is it's a fascinating dance to pull off. And I guess the way to do that is to just expand into all kinds of topics and play with ideas and then change your mind and all that kind of stuff.
Yeah, it's interesting because when people react against you by saying you are being arrogant about this, 99.999% of the time, all they mean is I disagree. Yeah. That's all they really mean, right?
Yeah.
Like at a very basic level, like people will accuse atheists of being arrogant. And I'm like, you think God exists and loves you, and you're telling me that I'm arrogant. I think that all of this is to say, just advice. When you disagree with somebody, try to specify the substantive disagreement. Try not to psychologize them, right? Try to say, oh, you're saying this because of this. Maybe it's true. Maybe you're right. But if you had an actual response to what they were saying, that would be much more interesting.
Yeah, I wonder why it's difficult for people to say or to imply, I respect you, I like you, but I disagree on this. And here's why I disagree. Like, I wonder why they go to this place of like, well, you're an idiot, or you're egotistical, or you're confused, or you're naive, or you're all the kinds of words, as opposed to like, I respect you as a fellow human being exploring the world of mysteries all around us, and I disagree.
I will complicate the question even more, because there's some people I don't respect or like. And I once wrote a blog post. I think it was called The Grid of Disputation. And I had a 2x2 grid, and it's, are you someone I agree with or disagree with? Are you someone who I respect or don't? Right? And all four quadrants are very populated. And so what that means is there are people who I like and I disagree with. And there are people who agree with me and I have no respect for at all. The embarrassing allies quadrant, that was everyone's favorite. So, and I just think being honest, right? Like trying to be honest about where people are. But if you actually want to move a conversation forward, forget about whether you like or don't like somebody. Explain the disagreement, explain the agreement. But you're absolutely right. I completely agree. Like, as a society, we are not very good at disagreeing. We instantly go to the insults.
Yeah, and I mean, even on a deeper level, I think at some deep level, I respect and love the humanity in the other person.
Yep.
Uh, you said that general relativity is the most beautiful theory ever.
So far.
What do you find beautiful about it?
Let's put it this way. When I teach courses, there's no more satisfying subject to teach than general relativity. And the reason why is because it starts from very clear, precisely articulated assumptions, and it goes so far, right? And, when I give my talk, you can find it online. I'm probably not going to give it again. The book, One of the Biggest Ideas talk, right, was building up from you don't know any math or physics. An hour later, you know Einstein's equation for general relativity. And the punchline is the equation is much smarter than Albert Einstein because Albert Einstein did not know about the Big Bang. He didn't know about gravitational waves. He didn't know about black holes, but his equation did. And that's a miraculous aspect of science more generally, but general relativity is where it manifests itself in the most absolutely obvious way.
A human question. What do you think of the fact that Einstein didn't get the Nobel Prize for general relativity?
Tragedy. He should have gotten maybe 4 Nobel Prizes, honestly.
That
he
one.
certainly should have got the photoelectric effect was 100% worth a Nobel Prize because, and people don't quite get this, who cares about the photoelectric effect? That's like this very minor effect. The point is his explanation for the photoelectric effect invented something called the photon. That's worth the Nobel Prize. Max Planck gets credit for this in 1900, explaining blackbody radiation by saying that when a little electron is jiggling in an object at some temperature, gives off radiation in discrete chunks rather than continuously. He didn't quite say that's because radiation is discrete chunks, right? It's like having a coffee maker that makes 1 cup of coffee at a time. It doesn't mean that liquid comes in 1 cup quanta, right? It's just that you are dispensing it like that. It was Einstein in 1905 who said light is quanta, and that was a radical thing. So that clearly, that was not a mistake. But also special relativity clearly deserved the Nobel Prize, and general relativity clearly deserved the Nobel Prize. Not only were they brilliant, but they were experimentally verified, like everything you want.
So separately, you think?
Yeah, absolutely.
Oh, humans.
Yeah.
Whatever the explanation there.
Edwin Hubble never won the Nobel Prize for finding the universe was expanding.
Yeah. But even the fact that we give prizes is almost kind of silly, and we limit the number of people that get the prize and all that.
I think that the Nobel Prize has enormous problems. I think it's probably a net good for the world because it brings attention to good science.
Yeah.
I think it's probably a net negative for science because it makes people want to win the Nobel Prize.
Yeah, there's a lot of fascinating human stories underneath it all. Science is its own thing, but it's also a collection of humans, and it's a beautiful collection. There's tension, there's competition, there's jealousy, but there's also great collaborations and all that kind of stuff. Daniel Kahneman, who recently passed, is one of the great stories of collaboration in science. So all of it, that's what humans do. And Sean, thank you for being the person that makes us celebrate science and fall in love with all of these beautiful ideas in science, for writing amazing books, for being legit and still pushing forward the research science side of it, and for allowing me and these pothead questions, and also for educating everybody through your own podcast. It's everybody should stop everything and subscribe and listen to every single episode of Mindscape. So thank you. I've been a huge fan forever. I'm really honored that you would speak with me in the early days when I was still starting this podcast. It means the world.
I appreciate it. Thanks very much for having me on. Now that you're a big deal, still having me on.
Thank you, Sean.